There is a rock hurtling through the darkness of space right now, at this very moment, following a path that crosses Earth's orbit. It is not particularly large. It would not fill a football stadium. You could walk across its surface in less than 10 minutes. And yet, this single lump of ancient stone forced humanity to do something it had never done before in all of recorded history: deliberately crash a spacecraft into another world, on purpose, at more than 14,000 miles per hour, just to see if we could push it. The rock is called Didymos. Its name comes from the Greek word for twin, and the reason for that name is itself one of the strangest discoveries in modern astronomy. Didymos is not alone. Orbiting around it, like a tiny moon circling a tiny planet, is a second rock, smaller, darker, and far more fragile than anyone expected. That second rock is called Dimorphos. And in September of 2022, a spacecraft the size of a vending machine slammed into Dimorphos at a speed that would carry you from New York to Los Angeles in roughly 10 minutes. The collision was intentional. It was the culmination of decades of worry, planning, argument, and engineering. And what happened next shocked nearly every scientist involved. But before we talk about what happened, we need to talk about why it happened at all. Because the story of Didymos is not really a story about one asteroid. It is a story about the terrifying mathematics of planetary defense, the field of science dedicated to one simple question: what do we do when a rock from space is heading straight for us? Here is the uncomfortable truth. The Earth has been hit before. It will be hit again. The only question is when. 66 million years ago, an asteroid roughly 10 kilometers across struck what is now the Yucatan Peninsula in Mexico, and in a matter of hours it ended the reign of the dinosaurs. That impact released energy equivalent to roughly 10 billion nuclear bombs detonating simultaneously. It punched a crater more than 180 kilometers wide into the Earth's crust. It sent a wall of superheated debris racing across the planet at thousands of kilometers per hour. It triggered earthquakes, tsunamis, and a blanket of dust so thick that sunlight was blocked for months. 75% of all species on Earth went extinct. Not in a century, not in a decade, in weeks. And here is the part that should keep you awake tonight. The asteroid that killed the dinosaurs was large. But Didymos and rocks like it do not need to be that large to cause a catastrophe. An object just 140 meters across, about the length of a city block, striking the Earth at typical asteroid velocities, could destroy an entire metropolitan area. It could generate shockwaves equivalent to hundreds of megatons of explosive force. It could trigger firestorms, flatten buildings across hundreds of square kilometers, and, depending on where it struck, send tsunamis racing across ocean basins. Dimorphos, the little moon orbiting Didymos, is roughly 160 meters across. That is large enough to qualify as a city killer. And Didymos itself, the parent body, is 780 meters wide. That is large enough to alter the climate of the entire planet. So when scientists say that Didymos is a potentially hazardous asteroid, they are not being dramatic. They are being precise. Its orbit brings it close enough to Earth, and it is large enough that it officially qualifies as a threat. Not today, not next year, but on timescales that matter, centuries, millennia. The mathematics of orbital mechanics make a close encounter almost inevitable. The universe does not care about our schedules. By the end of tonight, you're going to understand how this strange, tumbling, double-bodied asteroid was discovered, why it became the target of the most audacious planetary defense experiment ever attempted, and what the results of that experiment revealed. Not just about Dimorphos, but about the nature of asteroids themselves, about the fragility of our planet, and about humanity's first real attempt to change the course of the cosmos. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why Didymos matters, you first have to understand what asteroids are and where they come from. And to understand that, you have to go back to the very beginning, not just of the solar system, but of the cloud of gas and dust that existed before the solar system was even a possibility. 4.6 billion years ago, in a quiet arm of the Milky Way galaxy, there was nothing here, no sun, no Earth, no planets of any kind, just a vast, cold, slowly rotating cloud of molecular hydrogen, helium, and tiny grains of dust and ice, the leftover debris from stars that had lived and died long before. This cloud, known as the solar nebula, stretched across a region of space many times wider than the orbit of Pluto today. It was so thin, so diffuse, that a cubic meter of it contained fewer particles than the best vacuum chambers on Earth. And yet, within this almost nothing, gravity was at work. Something disturbed the cloud. Perhaps it was the shock wave from a nearby supernova, the death explosion of a massive star. Perhaps it was the gravitational tug of a passing molecular cloud. Whatever the trigger, one region of the nebula began to collapse inward. As it fell, it spun faster, the way a figure skater spins faster, by pulling in their arms. The center grew dense and hot, the edges flattened into a disk. And within that disk, a process began that would eventually produce everything you have ever known, everything you have ever touched, everyone you have ever loved. Tiny grains of dust and ice began to stick together. This process, called accretion, is deceptively simple in principle and staggeringly complex in practice. Two microscopic grains collide and stick. They attract a third, then a fourth. Over thousands of years, these clumps grow from specks to pebbles, from pebbles to boulders, from boulders to objects kilometers across. These intermediate bodies are called planetesimals, the building blocks of planets. And here is the key to understanding asteroids. Not all planetesimals became planets. Some of them were left behind. In the inner solar system, close to the young sun, planetesimals made of rock and metal merged into the four terrestrial planets: Mercury, Venus, Earth, and Mars. Farther out, beyond a boundary called the frost line, where temperatures dropped low enough for water and methane to freeze, planetesimals grew enormous. They captured thick atmospheres of hydrogen and helium, becoming the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. But between Mars and Jupiter, something went wrong. Jupiter, the largest planet in our solar system, grew so massive so quickly that its gravity became a bully. Its gravitational influence stirred the orbits of the planetesimals in the region between Mars and Jupiter, pumping energy into them, increasing their velocities, making their collisions more violent. Instead of gently merging into a planet, these objects smashed into each other at speeds that shattered them. They fragmented, they scattered, they were flung into eccentric, tilted orbits that prevented them from ever coalescing into a single world. The result is what we now call the asteroid belt, a vast ring of rocky debris stretching between roughly 2 and 3.5 astronomical units from the Sun, where 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. But here is the crucial point that most people get wrong about the asteroid belt. It is not a dense field of tumbling rocks, the way science fiction movies depict it. If you stood on any single asteroid in the belt and looked around, you would see almost nothing. The nearest neighboring asteroid would typically be millions of kilometers away. The total mass of every object in the asteroid belt combined is less than 4% of the mass of Earth's moon. It is a belt in name only, more like a scattering of lonely survivors in an impossibly vast space. And yet, within that scattering, there are millions of individual objects. Some are enormous. The dwarf planet Ceres, the largest object in the asteroid belt, is roughly 940 kilometers across, large enough to be roughly spherical under its own gravity. Others are tiny, barely more than pebbles tumbling through the void, and a significant number of them, more than we once imagined, do not stay in the belt. Gravitational interactions with Jupiter, close encounters with other asteroids, and a subtle but relentless force called the Yarkovsky effect. The tiny push an asteroid receives from the uneven way it radiates heat slowly nudge some of these objects onto new orbits. Orbits that bring them closer to the Sun, closer to Mars, and closer to Earth. These are the near-Earth objects. As of the mid-2020s, astronomers have catalogued more than 34,000 near-Earth asteroids. Most are small, most pose no immediate threat. But the sheer number of them, combined with the certainty that many more remain undiscovered, is what makes planetary defense scientists lose sleep, because finding them is only half the problem. The other half, the half that had never been tested until Didymos, is figuring out what to do about them. The asteroid that would eventually be named Didymos was discovered on April 11, 1996, by Joseph Montani, an astronomer working with the Spacewatch telescope at Kitt Peak National Observatory in Arizona. Spacewatch was one of the earliest dedicated programs for detecting near-Earth objects. It used a relatively modest telescope, a 0.9-meter reflector, but it was equipped with an electronic detector called a charge-coupled device, or CCD, that could capture faint objects invisible to photographic plates. Montani spotted a small streak of light moving against the fixed background of stars. Its motion identified it as something nearby, something in the inner solar system, something in an orbit that crossed the region of space where Earth travels. The object was given the provisional designation 1996 GT. At the time, it was just one more dot on a growing list. Nobody knew it had a companion. Nobody suspected it was anything special. The initial observations suggested a rocky body somewhere between several hundred meters and perhaps a kilometer across, moving on an orbit with a period of about 2.1 years, meaning it completed one trip around the Sun roughly every 25 months. Its orbit was eccentric, stretching from inside Earth's orbit to beyond the orbit of Mars, and its closest approaches to Earth, while not immediately dangerous, were close enough to earn it the official classification of a potentially hazardous asteroid. In the years that followed, additional observations refined the picture. Radar observations from the Goldstone Deep Space Communications Complex in California and from the Arecibo Observatory in Puerto Rico, two of the most powerful planetary radar facilities on Earth, revealed something unexpected. The radar echoes from the asteroid showed a peculiar pattern. The signal was not consistent with a single solid body. It flickered, it varied. It showed characteristics that suggested the object was not alone. In November of 2003, a team of astronomers led by Petr Pravec, a Czech researcher specializing in binary asteroids, published a study confirming what the radar data had hinted at. The asteroid, now designated 65803 Didymos, was a binary system. It had a moon. A tiny companion, less than one-fifth its size, was orbiting the primary body at a distance of roughly 1.2 kilometers, barely more than a kilometer separating the two. The orbital period of the moonlet was approximately 11 hours and 55 minutes. Every 12 hours, give or take, the little rock completed one full orbit around its parent. This was not as rare as it might sound. By the early 2000s, astronomers had begun to realize that binary asteroids were surprisingly common among near-Earth objects. Estimates suggested that roughly 15% of near-Earth asteroids larger than about 200 meters are binary or multiple systems. But Didymos was special for another reason. Its orbit, its size, and the geometry of its binary system made it an almost perfect target for something that a small but growing community of scientists had been arguing about for years: a kinetic impactor test, a deliberate, controlled experiment to see whether humanity could change the orbit of an asteroid by hitting it with a spacecraft. The idea was not new. As far back as the 1960s, scientists had discussed the theoretical possibility of deflecting an asteroid. Most early proposals involved nuclear weapons, detonating a warhead near or on the surface of an asteroid to either shatter it or push it off course. But nuclear deflection was fraught with problems. It was politically sensitive. It was technologically unproven in a real asteroid scenario. And worst of all, simulations suggested that a nuclear blast might simply break a loosely bound asteroid into multiple fragments, creating a shotgun blast of debris instead of a single object, potentially making the problem worse. The alternative, a kinetic impactor, was elegantly simple in concept. You build a spacecraft, you aim it at an asteroid, you crash it into the surface at high speed. The momentum transfer from the impact pushes the asteroid, ever so slightly, onto a different trajectory. Over time, if the deflection is performed years or decades before a potential Earth impact, that tiny nudge compounds. The asteroid misses Earth by thousands or even millions of kilometers. No nuclear weapons, no exotic technology, just physics, Newton's laws applied at interplanetary scale. But here is the problem. Nobody had ever actually tried it. The concept existed only in computer simulations and academic papers, and the simulations revealed a disturbing uncertainty. The amount of deflection you get from a kinetic impact depends enormously on the composition and structure of the asteroid. A solid chunk of iron and nickel would respond very differently from a loosely packed pile of rubble held together by little more than its own feeble gravity. And at the time, scientists did not know, could not know, which type of asteroid they might someday need to deflect. This is where the story of Didymos transforms from a discovery story into something much more urgent. Because in the early 2000s, a team at the Johns Hopkins University Applied Physics Laboratory, the same institution that had built the near Shoemaker spacecraft, which became the first probe to orbit and land on an asteroid in 2000, began designing a mission that would answer the question once and for all. They called it DART, the Double Asteroid Redirection Test. The concept was audacious. Launch a spacecraft to the Didymos system. Aim it not at Didymos itself, the larger body, but at Dimorphos, the moonlet. Crash DART into Dimorphos at roughly 6.6 kilometers per second, more than 23,000 kilometers per hour, and then measure how much the impact changed Dimorphos' orbit around. Didymos. The beauty of targeting a binary system was measurement. If you hit a solitary asteroid and nudge it, measuring the change in its orbit around the Sun requires extraordinarily precise tracking over months or years. But if you hit a moonlet orbiting a primary, you can measure the change in the moonlet's orbital period almost immediately, simply by watching how it moves relative to the larger body. Didymos was the perfect laboratory, close enough to reach, small enough that the moonlet's orbit could be measurably changed, and hazardous enough that the experiment was not merely academic. It was a rehearsal for a scenario that might one day be terrifyingly real. But before DART could launch, scientists needed to understand their target far better than they did. What was Didymos made of? What was its internal structure? Was it a solid monolith, a fractured slab, or something else entirely? The answers to these questions would determine not just whether DART succeeded, but what the results would mean for the future of planetary defense. And the answers, when they finally came, were not what anyone expected. The problem with asteroids, the deep, fundamental problem that has haunted planetary defense scientists since the field began, is that we do not truly understand what they are made of. Not in the way that matters. We know their broad chemical classifications. We know that some are rich in carbon and organic compounds, dark and primitive, virtually unchanged since the solar system formed. We know others are stony, composed of silicate minerals like olivine and pyroxene. We know a smaller number are metallic, dominated by iron and nickel, the exposed cores of ancient planetesimals that were shattered by collisions billions of years ago. But knowing what an asteroid is made of is not the same as knowing how it is put together. And that distinction between composition and structure turns out to be the difference between life and death when you are trying to deflect one. To understand why, imagine two objects sitting on a table in front of you. One is a solid brick. The other is a pile of gravel, loosely stacked into the same shape and roughly the same size as the brick. If you throw a baseball at the brick, the energy transfers cleanly. The brick slides across the table. The momentum from the baseball pushes it in a predictable direction by a predictable amount. Now throw the same baseball at the gravel pile. What happens? The baseball buries itself. Some gravel scatters. The pile deforms. Some momentum transfers to the pile as a whole, but a significant portion is absorbed by the rearrangement of the gravel itself. Fragments shifting, sliding, compacting. The pile barely moves. This, in essence, is the nightmare scenario for kinetic deflection. If the asteroid you need to deflect is a solid body, a kinetic impactor works beautifully. The momentum transfer is efficient. The asteroid moves. But if the asteroid is what scientists call a rubble pile, a loose collection of boulders, pebbles, and dust held together primarily by its own weak gravity and perhaps by very faint cohesive forces, then the efficiency of a kinetic impact drops dramatically. The impactor buries itself. The energy is absorbed. The asteroid barely flinches. And here is the unsettling reality that emerged from decades of observation. Most asteroids, particularly those in the size range most relevant to planetary defense, appear to be rubble piles, not solid monoliths, not coherent slabs of stone, piles of debris loosely bound, structurally more like beanbags than boulders. The evidence accumulated steadily through the 1990s and 2000s. In 1997, the near-Shoemaker spacecraft flew past the asteroid 253 Mathilde and found an object so porous, so underdense, that it could not possibly be solid rock. Its density was roughly 1.3 grams per cubic centimeter, far below the density of the silicate minerals it was composed of. The implication was clear. Mathilde was riddled with voids. It was not a rock, it was a sponge. In 2003, the Japanese spacecraft Hayabusa arrived at the asteroid Itokawa and found something even more startling. Itokawa looked like a battered peanut, covered in boulders and gravel, with no visible craters of significant size. The absence of craters was the key clue. On a solid body, impacts leave craters that persist for billions of years. On a rubble pile, impacts send shockwaves through the loose interior, causing the surface to shift and rearrange, effectively erasing the evidence. Itokawa was not a rock that had been scarred by impacts. It was a pile of rubble that had been shaken by them. And then, in 2018 and 2019, 2 missions arrived at 2 different asteroids and confirmed the rubble pile model in breathtaking detail. NASA's OSIRIS-REx spacecraft reached the asteroid Bennu, and JAXA's Hayabusa 2 reached the asteroid Ryugu. Both asteroids were roughly 500 meters across. Both were shaped like spinning tops, a distinctive form that arises when a loosely bound body spins fast enough to push material toward its equator. And both were covered in boulders. Not fine regolith, not smooth dust, boulders. Enormous, jagged, precariously balanced boulders, some as large as houses, littering surfaces that looked less like a planetary body and more like a construction site. The images from Bennu were particularly alarming for the planetary defense community. OSIRIS-REx was designed to collect a sample from Bennu's surface, and the mission team had expected to find at least some smooth, fine-grained areas suitable for the sampling maneuver. They found almost none. The surface was so rough, so chaotic, so densely packed with boulders, that the team had to completely redesign their approach. They eventually targeted a crater called Nightingale, one of the few spots where fine material had accumulated, and even there, the margins were dangerously tight. But the boulders were not the most unsettling discovery. The density measurements were. Bennu's bulk density was approximately 1.19 grams per cubic centimeter. The minerals that compose Bennu have an intrinsic density of roughly 2.5 to 3 grams per cubic centimeter. The only way to reconcile those numbers is if Bennu is roughly 25 to 40% empty space by volume. It is a flying rubble heap, boulders and pebbles and dust with enormous gaps between them, held in a roughly spherical shape by gravity so weak that an astronaut standing on the surface would weigh about as much as a sheet of paper weighs on Earth. Let that sink in. The object that the planetary defense community might someday need to deflect is not a cannonball. It is a house of cards. This realization transformed the DART mission from an interesting experiment into an urgent necessity. Because if Dimorphos, the moonlet of Didymos, the actual target of the DART impact, was also a rubble pile, then the results of the kinetic impact test would be fundamentally different from what simulations based on solid body assumptions had predicted, and the implications would ripple through every planetary defense plan on Earth. But here is the problem. Before DART launched, scientists did not know Dimorphos' internal structure. They had never seen it up close. Ground-based radar observations had confirmed its existence and measured its orbital period around Didymos to remarkable precision, 11 hours and 55 minutes, plus or minus about 2 minutes. They knew its approximate size, roughly 160 meters across. They knew it was tidally locked to Didymos, always showing the same face to its parent, the way our moon always shows the same face to Earth. But they did not know whether it was solid, fractured, or a rubble pile. They did not know its density. They did not know the size distribution of rocks on its surface. They were, in a very real sense, aiming a spacecraft at a target they did not fully understand, and it gets worse. The physics of a kinetic impact on a rubble pile asteroid is not just uncertain, it is potentially counterintuitive. When DART struck Dimorphos, it would transfer its momentum to the moonlet. That much was guaranteed by Newton's third law, but the total change in Dimorphos' velocity would depend on something called the momentum enhancement factor, often written by scientists as the Greek letter beta. If DART struck a solid surface and simply cratered, transferring its momentum and nothing else, beta would equal approximately 1. The asteroid would receive a push equal to the momentum of the spacecraft itself. But if the impact excavated material, if it blasted rocks, dust, and debris off the surface of Dimorphos and sent them flying back into space, then those ejected fragments would carry momentum in the opposite direction, creating an additional push on the asteroid. It would be like the recoil of a cannon. The spacecraft is the cannonball going one way, and the ejected debris acts as a second cannonball going the other way. In that case, beta could be significantly greater than 1, potentially 2, 3, even higher. But the reverse was also possible. If Dimorphos was very loosely packed, very porous, the impactor might simply bury itself. The kinetic energy would be absorbed by the compaction of the rubble. Little material would be ejected. Beta could be close to 1, or even slightly less. The impact would be absorbed like a bullet hitting sand. The uncertainty in beta was not a minor academic concern. It was the central unknown in the entire planetary defense strategy. A beta of 1 meant that deflecting a threatening asteroid would require a very large, very expensive spacecraft, or multiple impacts. A beta of 3 or 4 meant that a much smaller impactor could do the job, making planetary defense feasible with existing technology. The difference between those two scenarios was the difference between a problem humanity could solve and a problem that might be unsolvable within the warning time available. This is not science fiction. This is the calculation that determines whether a kinetic impactor can save a city. The DART mission was designed to measure beta, not to estimate it, not to model it, to measure it directly by watching what happened when a real spacecraft hit a real asteroid at real interplanetary speeds. And that meant everything about the mission had to work. The navigation had to be precise enough to hit a target 160 meters wide from more than 10 million kilometers away. The impact had to occur at the right angle, at the right speed, in the right location on Dimorphos' surface. The observations from ground-based telescopes, from the Hubble Space Telescope, from the James Webb Space Telescope, and from a tiny companion CubeSat called Lycia Cube that would fly past Dimorphos minutes after the impact, all had to capture the event with sufficient detail to measure the change in orbital period. And the entire mission rested on one terrifying assumption, that the predictions about how rubble pile asteroids respond to impacts were at least approximately correct. Because if they were wrong, if the real physics of the impact differed dramatically from the models, then the mission might succeed as a technology demonstration, but fail as a guide for planetary defense. Humanity would crash a spacecraft into an asteroid, measure the result, and realize that the result told them nothing useful about what to do next. This was the tension at the heart of the DART mission. It was not merely an engineering challenge, it was a scientific gamble. The spacecraft had to work, but more importantly, the universe had to cooperate. The lead-up to launch was fraught with the kind of quiet, grinding anxiety that rarely makes headlines. The DART spacecraft was not large. It weighed roughly 610 kilograms at launch, about the mass of a grand piano. It was roughly the size of a large refrigerator, with 2 enormous roll-out solar arrays, each about 8.5 meters long, deployed to power its ion propulsion system during the cruise. It carried no scientific instruments designed to study Dimorphos in detail. It carried one camera, a single high-resolution imager called Draco, the Didymos reconnaissance and asteroid camera for optical navigation, and its primary purpose was not science but navigation. Draco's job was to guide the spacecraft to its target in the final hours and minutes of the approach, when the ground team would no longer be able to send commands fast enough to correct course. In the last 4 hours before impact, DART would be on its own. Its onboard autonomous navigation system, called Smart Nav, would identify Dimorphos, distinguish it from the larger Didymos, lock onto it, and steer the spacecraft to a direct hit. Think about what that means for a moment. A spacecraft traveling at 6.6 kilometers per second, roughly 4 miles per second, approaching a target that no camera had ever seen up close, distinguishing that target from its parent body in real time, and steering itself to a collision with no human intervention possible. The light time delay between Earth and the Didymos system at the time of impact was roughly 38 seconds in each direction. By the time any correction signal from Earth could reach the spacecraft, it would have travelled nearly 500 kilometers past the point where the correction would have mattered. DART launched on November 24, 2021 from Vandenberg Space Force Base in California aboard a SpaceX Falcon 9 rocket. For the next 10 months, it cruised through interplanetary space, gradually closing the distance to the Didymos system. During the cruise, the mission team tested SmartNav, calibrated Draco, and refined their trajectory. They also watched with increasing anticipation as the Didymos system grew from an indistinct point of light into something resolvable. But here is what makes this truly terrifying. Even with all the preparation, all the testing, all the simulations, no one knew exactly what DART would find when it arrived. The best radar images of Dimorphos from Earth showed a fuzzy blob. Its shape was unknown, its surface was unknown. Whether it was a smooth ellipsoid, a jagged shard, or a lumpy pile of boulders. All of that was hidden behind the veil of distance until the very last moments before impact. DART would see its target clearly for the first time only minutes before it was destroyed by the collision. On September 26, 2022, at 7:14 p.m. Eastern Daylight Time, DART's Draco camera began returning images that changed everything. The Didymos system swam into view, first as a single point of light, then as two distinct objects, then, in the final minutes, as two worlds in miniature. Didymos, the parent body, was shaped roughly like a spinning top, an oblate spheroid with a pronounced equatorial ridge, its surface strewn with boulders. But it was Dimorphos that seized everyone's attention. The images came in faster and faster as the spacecraft closed in. Each frame showed more detail than the last, and with each new image, the scientists watching in real time felt a growing sense of astonishment and dread. Dimorphos was not what they had expected. It was not a smooth ellipsoid. It was not a featureless egg. It was a rubble pile of the most extreme kind, a loose, chaotic assemblage of boulders with virtually no fine-grained material visible on its surface. It looked, as one mission scientist later described it, like a pile of rocks in a parking lot. The boulders were everywhere. They ranged in size from less than a meter to more than 6 meters across. Some appeared to be resting loosely on the surface, barely held in place by the asteroid's negligible gravity. Dimorphos's surface gravity is roughly 100,000 times weaker than Earth's. An astronaut standing on Dimorphos could have jumped and entered orbit. The boulders were not cemented together. They were not embedded in a matrix of finer material. They were simply sitting there, a jumble of fragments that happened to be gravitationally bound. Something is wrong with our assumptions, the data seemed to say. The models that predicted what Dimorphos would look like had anticipated a more cohesive body, something with at least some regolith, some fine dust, some evidence of surface processes. What DART found instead was an object that appeared to be barely holding itself together, an object that, under slightly different circumstances, a faster spin, a slightly larger impact, a different orbital resonance, might simply fly apart. At 7:14 p.m. In approximately 30 seconds, the Draco camera captured its final image. In that image, Dimorphos's surface filled the entire frame. Individual boulders were visible in sharp detail, their shadows crisp in the low sunlight. The image was breathtaking in its clarity and terrible in its implication. This was the last thing DART ever saw. Less than a second after this image was taken, the spacecraft struck Dimorphos at 6.1 kilometers per second. The signal from DART went silent. In mission control at the Johns Hopkins Applied Physics Laboratory, there was a moment of absolute silence. Then applause erupted. The spacecraft had hit its target. The first step was complete. But the real question, the question that would determine whether this mission mattered for the future of civilization, had not yet been answered. How much did Dimorphos move? The hours that followed the impact were some of the most intense in the history of planetary science. Telescopes around the world and in orbit above it had been watching the Didymos system in anticipation. The Hubble Space Telescope, the James Webb Space Telescope, ground-based observatories in Chile, Hawaii, South Africa, and the Canary Islands, dozens of instruments, all pointed at the same tiny point of light. all waiting for the flash. And they got far more than a flash. They got a spectacle. Within seconds of the impact, a massive plume of debris erupted from Dimorphos. Not a small puff, not a gentle cloud, a vast cone-shaped spray of pulverized rock, dust and boulder fragments that expanded outward from the impact site at hundreds of meters per second. The Hubble Space Telescope captured images of the debris plume evolving over hours, then days. It grew, it stretched, it formed complex structures, twin tails, like a comet, extending thousands of kilometers behind Dimorphos as the pressure of sunlight pushed the finest particles outward. The amount of material ejected was staggering. Initial estimates suggested that DART's impact had blasted more than 1 million kilograms of rock and dust off Dimorphos's surface. 1 million kilograms. The spacecraft itself weighed roughly 570 kilograms at the time of impact. It had ejected more than 1,000 times its own mass in debris, and all of that debris, flying outward from the surface, had carried momentum with it. Momentum that acted as an additional push on Dimorphos, augmenting the direct momentum transfer from the spacecraft itself. This was the cannon recoil effect that scientists had hoped for, but the magnitude was far beyond most predictions. The ground-based observation campaign that followed was the largest coordinated asteroid observation effort in history. More than 40 telescopes on 5 continents participated, along with both Hubble and the James Webb Space Telescope. Their task was conceptually simple but observationally demanding. Measure the new orbital period of Dimorphos around Didymos and compare it to the pre-impact period. The difference would reveal exactly how much DART had changed Dimorphos's orbit, and from that change, scientists could calculate beta, the momentum enhancement factor that was the entire point of the mission. The result, announced on October 11, 2022, just 2 weeks after the impact, sent shockwaves through the planetary defense community. Before the impact, Dimorphos orbited Didymos every 11 hours and 55 minutes. After the impact, the orbital period was 11 hours and 23 minutes. DART had shortened Dimorphos's orbital period by 32 minutes. The pre-mission success threshold, the minimum change that NASA had defined as a successful demonstration, was 73 seconds. 73 seconds. DART had achieved a change of 32 minutes. It had exceeded the minimum success criterion by a factor of more than 25. The numbers are striking. The change in orbital period implied a velocity change, a delta V, for Dimorphos of roughly 2.7 millimeters per second. That sounds impossibly small. 2.7 millimeters per second. Slower than a snail. But remember, in the context of planetary defense, what matters is not the immediate speed change, but the cumulative effect over time. If a threatening asteroid were nudged by just 2.7 millimeters per second years before its projected Earth impact, the deflection would accumulate with every orbit, gradually widening the gap between the asteroid's path and Earth's position at the time of the potential collision. Over a decade, that tiny nudge could translate into a missed distance of thousands of kilometers. But the most remarkable finding was not the orbital period change itself. It was what the orbital period change implied about beta. The momentum enhancement factor for the DART impact on Dimorphos was calculated to be approximately 3.6. That means the total momentum transferred to Dimorphos was 3.6 times the momentum of the spacecraft alone. The ejected debris, that vast plume of rock and dust, had contributed more than 2.5 times as much momentum as the spacecraft itself. The recoil from the debris was the dominant effect, not the direct hit. This was extraordinary, and it was deeply encouraging for planetary defense. A beta of 3.6 meant that kinetic impactors were far more effective than the conservative models had predicted. It meant that smaller spacecraft, launched with less energy, could achieve meaningful deflections. It meant that the window of time needed to mount a successful deflection campaign was potentially shorter than feared. In practical terms, a beta of 3.6 made planetary defense feasible with technology that exists today. But here is the problem. That single number, 3.6, also revealed something deeply unsettling about Dimorphos itself. A beta that high implied that an enormous amount of material had been loosened and ejected by the impact. That material had to come from somewhere. and the only way so much debris could be liberated by a relatively small impactor was if Dimorphos's surface, and possibly its entire structure, was far more loosely bound than even the rubble pile models had suggested. Dimorphos was not just a rubble pile, it was in some sense barely an object at all. It was a gravitational aggregate, a collection of fragments so weakly held together that a collision with a spacecraft weighing less than a small car could fundamentally reshape it. Later analysis of the Lycia cube images and the debris plume dynamics suggested that the impact may not have merely cratered the surface, it may have deformed the entire body. The shape of Dimorphos may have changed, its mass distribution may have shifted. The very definition of what Dimorphos was before the impact may no longer apply to what Dimorphos is after it. And this is where the answer becomes deeply unsettling. Because if the asteroids most likely to threaten Earth are this fragile, this loosely held, this responsive to impacts, then every plan, every simulation, every strategy for deflection must account for the possibility that the asteroid might not simply move. It might change shape, it might shed mass, it might fragment. The line between deflection and destruction is blurrier than anyone wanted to admit. The question of asteroid structure is not merely academic, it is, in the most literal sense, existential. And the story of how scientists came to understand, and then to fear, the rubble pile model is one of the most important chapters in the history of planetary science. It begins, as so many stories in science do, with a prediction that turned out to be wrong. For most of the 20th century, the prevailing model of asteroids was simple. They were rocks. Big, solid, dense rocks. Fragments of larger bodies that had been shattered by ancient collisions. The leftover rubble of planet formation, toughened. This model was intuitive. It was consistent with the meteorites that fell to Earth. Dense chunks of stone or iron that had survived the violent passage through the atmosphere. If the pieces that reached the ground were solid, the reasoning went, then the parent bodies they came from must have been solid too. But in the 1970s and 80s, a slow revolution began. Astronomers started measuring the rotation rates of asteroids, how fast they spin, and they discovered something puzzling. Small asteroids, those less than roughly 150 meters across, could spin incredibly fast. Some completed a full rotation in just a few minutes. But larger asteroids, those above about 150 meters, seemed to obey a speed limit. None of them spun faster than about one rotation every 2.2 hours. This boundary, which came to be known as the spin barrier, or the rubble pile spin limit, was a revelation. The explanation was elegant and disturbing. A solid body can spin as fast as its structural strength allows. The tensile strength of rock can resist centrifugal forces even at very high rotation rates. But a body held together only by gravity, a rubble pile, has no tensile strength. If it spins too fast, the centrifugal force at its equator exceeds the gravitational pull, and the body tears itself apart. Material flies off, the body disintegrates. The spin barrier at roughly 2.2 hours corresponds to the critical rotation rate for a body held together solely by its own gravity, with no internal cohesion. The fact that virtually all asteroids larger than 150 meters respect this speed limit was powerful evidence that they are rubble piles. Solid bodies would be scattered randomly across the spin rate chart. Rubble piles would cluster below the barrier, and that is exactly what the data showed. Didymos itself provided further evidence. Its rotation period is approximately 2.26 hours, right at the edge of the spin barrier. It is spinning almost as fast as a rubble pile of its density possibly can without flying apart. Its oblate shape, with that pronounced equatorial ridge, is consistent with a body that has been spun up to its structural limit, with material migrating toward the equator under the combination of centrifugal force and gravity. Didymos looks, in every measurable way, like a rubble pile that is barely holding itself together. And this leads to one of the most fascinating questions about the Didymos system. Where did Dimorphos come from? How did the parent body acquire a moon? The answer, according to the leading hypothesis, is that Didymos made Dimorphos. Not through capture. The gravitational dynamics of capture in the asteroid belt are extraordinarily unlikely for objects this small. Not through a catastrophic collision. There is no evidence of a massive impact event. The most widely accepted model is called the Yorp effect, and it is one of the most beautiful examples of how a seemingly negligible force can reshape worlds. The Yarkovsky-O'Keefe-Rajewsky-Paddock effect, Yorp for short, is the rotational counterpart to the Yarkovsky effect. While the Yarkovsky effect changes an asteroid's orbit by creating a tiny thrust from the uneven emission of thermal radiation, the Yorp effect changes an asteroid's spin rate through the same mechanism. An irregularly shaped asteroid absorbs sunlight on its surface and re-emits that energy as thermal infrared radiation. Because the shape is irregular, the radiation is not emitted symmetrically. The net effect is a tiny torque, a rotational push, that, over millions of years, can either spin the asteroid up or slow it down. For Didymos, the Yorp effect appears to have spun it up. Slowly, relentlessly, over millions of years, sunlight exerted a torque on the irregularly shaped body, increasing its rotation rate fraction of a revolution at a time. As the spin rate increased, the centrifugal force at the equator grew. Material began to shift. Loose regolith migrated toward the equatorial ridge. The body became more oblate, and eventually the centrifugal force at the equator exceeded the local gravitational pull. Material began to lift off, not explosively, not dramatically, gently. Particles of regolith, small pebbles, and fragments of rock slowly drifted away from the spinning equator, entering orbit around the parent body. Over time, this orbiting debris coalesced, accreted, just as the planetesimals had billions of years earlier, into a single companion body, a moonlet, Dimorphos. If this model is correct, and the evidence strongly supports it, then Dimorphos is not merely an object that orbits Didymos. It is a piece of Didymos. It is the parent body's own material, shed and reassembled. Mother and child are made of the same substance, born from the same ancient planetesimal, separated by a force as gentle as sunlight. There is something both poetic and unsettling about this picture. The same gentle force that warms our faces on a spring morning, sunlight, can given enough time, tear an asteroid apart and create a new world from the debris. The universe does not discriminate between gentle and destructive. It simply applies forces and weights. By the time the DART mission was being planned in the early 2010s, the Didymos system had become one of the best characterized binary asteroid systems known. Radar observations from Goldstone and Arecibo had measured the sizes, shapes, and orbital parameters of both bodies with remarkable precision. Light curve observations, measurements of how the total brightness of the system varied as the two bodies orbited each other and alternately eclipsed and blocked each other's light, had nailed down the mutual orbit to an accuracy of seconds. Thermal infrared observations from the Spitzer Space Telescope had constrained the surface properties and albedo, the reflectivity, of both objects. The picture that emerged was this. Didymos is a roughly oblate spheroid, about 780 meters across at its widest, spinning on its axis once every 2.26 hours. Its surface is covered in boulders and rough regolith, consistent with a rubble pile structure. Its density is approximately 2.17 grams per cubic centimeter, below the density of its constituent minerals, confirming internal porosity. Dimorphos, the moonlet, orbits at a center-to-center distance of about 1.2 kilometers, completing one orbit in 11 hours and 55 minutes. It is approximately 160 meters across, roughly egg-shaped and, as DART would eventually confirm, composed of loosely packed boulders. But all of these measurements, precise as they were, could not answer the question that mattered most. What would happen when you hit Dimorphos at 6.5 kilometers per second? That question required a mission. And that mission required something that is perhaps the rarest commodity in the history of space exploration: institutional patience. The DART concept was first proposed in the early 2000s. It was studied, reviewed, shelved, resurrected, restudied, and re-reviewed over the course of more than a decade. The path from concept to approval to funded mission to launch was not a straight line. It was a winding road through the bureaucratic landscape of NASA, the scientific review panels, the congressional budget cycles, and the competing demands of other missions. There were moments when DART almost did not happen. Moments when budget pressures threatened to delay it indefinitely. Moments when the scientific community debated whether the money would be better spent on discovery. finding more asteroids, rather than deflection, learning to push them. The argument was not unreasonable. After all, you cannot deflect an asteroid you have not found. But the counter-argument was equally compelling. Finding an asteroid headed for Earth without knowing how to stop it would be the cruelest discovery in human history. In the end, DART was approved, funded, and built. It launched in 2021, it flew for 10 months, and on September 26, 2022, it accomplished something that no human civilization in the 4.5 billion year history of this planet had ever done before. It changed the orbit of a celestial body, not by much, not by a lot, by 32 minutes, a tiny fraction of Dimorphos's orbital period. But that tiny fraction, multiplied by the vast distances of space and the long timelines of orbital mechanics, was the proof that planetary defense is not a fantasy, it is a capability. A demonstrated, measured, quantified capability. But here is what makes this truly terrifying. The DART mission answered one question: can we change an asteroid's orbit? And in doing so, it opened a dozen more. What happens if the asteroid is larger? What happens if the warning time is shorter? What happens if the asteroid is not a rubble pile, but a solid, metallic body? What happens if the impact shatters the asteroid into fragments? What happens if 2 fragments hit Earth instead of 1? What if the beta value is different for different types of asteroids? And we do not know which type we are facing until it is too late to choose a different strategy. These are not hypothetical questions. They are the questions that planetary defense scientists are working to answer right now, today, using the data from DART and preparing the next generation of missions. The most important of these is Hera, the European Space Agency's follow-up mission to the Didymos system, which launched in October of 2024 and is expected to arrive at Didymos in late 2026. Hera will do what DART could not. It will study the aftermath. It will measure the crater left by DART's impact. It will map the surface of Dimorphos in detail. It will deploy 2 small CubeSats to take close-up measurements of both bodies. And it will determine, with far greater precision than ground-based observations alone can achieve, exactly what DART did to Dimorphos, not just to its orbit, but to its shape, its mass, its structure. The story of Didymos is far from over. In many ways, it has only just begun. To fully grasp the scale of the problem that Didymos represents, it helps to understand just how recently humanity became aware of near-Earth asteroids at all. The history of our awareness is humblingly short. For most of human civilization, the idea that rocks could fall from the sky was considered absurd. In the 18th century, when reports of stones falling from the heavens reached the scientific academies of Europe, they were dismissed as folklore, superstition, or outright delusion. The great chemist Antoine Lavoisier, one of the founders of modern chemistry, famously argued that stones could not fall from the sky because there are no stones in the sky. The idea was simply incompatible with the Enlightenment understanding of the cosmos. It was not until 1803, when a spectacular meteorite fall near the French town of L'Aigle showered thousands of stones across the countryside, that the French Academy of Sciences sent the young physicist Jean-Baptiste Biot to investigate. Biot's meticulous report, documenting the trajectory, the distribution of stones, and the eyewitness accounts, finally convinced the scientific establishment that extraterrestrial objects could, and did, fall to Earth. But even after meteorites were accepted as real, the idea that large asteroids could strike the Earth with catastrophic consequences took another century and a half to emerge. The defining moment came in 1980, when Luis and Walter Alvarez, a father-son team at the University of California, Berkeley, published a paper proposing that the mass extinction at the end of the Cretaceous period, the event that killed the dinosaurs, was caused by an asteroid impact. Their evidence was an anomalous layer of the element iridium found in rock formations dating to 66 million years ago. Iridium is rare on Earth's surface, but common in asteroids. The iridium layer, found at sites around the world, was the smoking gun of a cosmic collision. The Alvarez hypothesis was initially controversial. Many geologists favored volcanic activity as the cause of the extinction, but the discovery of the Chicxulub crater on the Yucatan Peninsula in the early 1990s A buried impact structure more than 180 kilometers across, dating precisely to the end of the Cretaceous, sealed the case. An asteroid roughly 10 to 15 kilometers across had struck the Earth and ended an era. This discovery electrified the planetary defense community, which, at the time, barely existed. A handful of astronomers had been quietly tracking near-Earth objects since the 1970s, using small telescopes and shoestring budgets. But the confirmation that asteroid impacts could cause mass extinctions transformed the field from a backwater into a priority. In 1998, the United States Congress directed NASA to discover and catalogue 90% of all near-Earth objects larger than 1 kilometer within 10 years. This mandate spawned a generation of asteroid survey programs. Lincoln Near-Earth Asteroid Research, or LINEAR, at the Massachusetts Institute of Technology's Lincoln Laboratory, the Catalina Sky Survey at the University of Arizona, Pan-STARRS in Hawaii, and eventually the next-generation surveys that would discover tens of thousands of smaller objects. It was in this environment of growing awareness and growing anxiety that Didymos was discovered. 1996, 2 years before Congress issued its mandate. The world was only just waking up to the realization that the night sky was not as empty and benign as it appeared. And the timing matters because it sets the stage for a question that would define the next 2 decades of planetary science. Now that we are finding these objects, what exactly are we going to do about them? The challenge of planetary defense is often compared to an insurance policy. You pay a premium, in this case, the cost of detection programs and deflection technology development, to protect against a low-probability, high-consequence event. But the analogy breaks down in a crucial way. With insurance, you know roughly what the threats look like. You know how fires spread, how floods rise, how earthquakes shake buildings. With asteroids, until very recently, we did not know what the threats looked like at all. We did not know their shapes, their structures, their internal properties. We did not know how they would respond to our attempts to move them. We were buying insurance against a hazard we could not fully describe. Didymos changed that. Not entirely, not completely, but fundamentally. For the first time, humanity had a data point, a real, physical measured result of a kinetic impact on a real asteroid. And that single data point was worth more than 1,000 computer simulations, because it revealed something the simulations had not predicted. The beta value of 3.6 was higher than most models had estimated for a rubble pile target. The ejector plume was more massive, more energetic, more sustained than expected. The interaction between the impactor and the rubble pile surface was more complex, more violent, and more productive than the models had foreseen. But it also raised a concern that few people outside the planetary defense community have fully reckoned with. The DART experiment was conducted on a moonlet orbiting a parent body. It was not conducted on a solitary asteroid in heliocentric orbit. The orbital mechanics of the binary system provided a convenient measurement framework, but they also introduced complexities. The gravitational interaction between Dimorphos and Didymos, the tidal forces, the exchange of ejecta between the two bodies. All of these factors influence the outcome in ways that might not apply to a solitary asteroid scenario. Extrapolating from the DART result to a real deflection campaign requires careful accounting of these differences. And there is another factor, one that is rarely discussed publicly, but that keeps planetary defense engineers awake at night. The DART impact occurred under ideal conditions. The trajectory was known years in advance. The target was well characterized. The spacecraft had months to refine its approach. The impact geometry, the angle between the spacecraft's velocity vector and Dimorphos's orbital motion, was close to optimal. In a real emergency, none of these conditions might hold. A threatening asteroid might be discovered only months or years before its projected impact. Its orbit might be poorly constrained. Its size and structure might be unknown. The deflection mission would need to be designed, built, launched, and targeted in a fraction of the time that DART enjoyed. This is the paradox of planetary defense. We have demonstrated that deflection is possible, but the conditions under which deflection might actually be needed are almost certain to be far more challenging than the conditions under which it was tested. DART was a proof of concept, A real deflection campaign would be a test of everything: our detection capabilities, our launch readiness, our navigation precision, our understanding of asteroid physics, and, perhaps most importantly, our ability to make decisions under existential pressure. And so the story of Didymos is not just a story about an asteroid or a mission or a measurement. It is a story about the razor-thin margin between civilization as we know it and a catastrophe we cannot undo. It is a story about the first time humanity reached out and touched the trajectory of another world. Not to explore it, not to study it, but to survive it. That story is now inseparable from the story of Dimorphos, the child of Didymos, the tiny moonlet born from sunlight and gravity, shaped by forces older than memory, and struck by a machine built by a species that has existed for the blink of a cosmic eye. What happened to Dimorphos when Dart struck it, and what happened afterward, is where the story turns from science into something closer to revelation. There is a number that planetary defense scientists return to again and again, a number that frames the entire conversation about asteroids and human survival. That number is approximately 1,000. As of the mid-2020s, roughly 1,000 near-Earth asteroids larger than 1 kilometer in diameter have been discovered. These are the civilization enders. Objects large enough that an impact with Earth would cause global catastrophe, blocking sunlight, collapsing agriculture, potentially ending human civilization as we know it. The good news is that more than 95% of these large objects are believed to have been found. Their orbits have been calculated. None of them poses a significant threat within the next century. But 1 kilometer is a high bar for destruction. Objects far smaller than that can cause devastation on a regional or even continental scale. An asteroid 300 meters across striking the Earth would release energy equivalent to roughly hundreds of megatons of TNT, dwarfing the largest nuclear weapon ever detonated. An asteroid 140 meters across, roughly the size of Dimorphos, could destroy a city. And below that threshold, objects of 50 to 100 meters can produce airbursts powerful enough to flatten forests and shatter windows across thousands of square kilometers, as the Tunguska event demonstrated in 1908, when a small asteroid or comet fragment exploded above Siberia with the force of roughly 5 to 15 megatons, flattening more than 2,000 square kilometers of forest. The problem is that most of these smaller objects have not been found. Of the estimated 25,000 near-Earth asteroids larger than 140 meters, only about 40% have been discovered and tracked. That means roughly 15,000 objects large enough to destroy a city are orbiting in the inner solar system right now, and we do not know where they are. We do not know their sizes. We do not know their orbits. We do not know whether any of them will intersect Earth's path next year, or next decade, or next century. And it gets stranger. Below 140 meters, the picture becomes even murkier. There may be millions of near-Earth objects in the 20 to 140 meter range, the size range that produced the Tunguska event, the size range that could devastate a metropolitan area. Fewer than 5% of these are estimated to have been discovered. Millions of objects, untracked, unseen, invisible against the vast black backdrop of space, any one of which could appear in our sky with little or no warning. The Chelyabinsk event of February 15, 2013, drove this point home with brutal clarity. A small asteroid, roughly 20 meters across, barely a pebble by cosmic standards, entered Earth's atmosphere above the Russian city of Chelyabinsk at a speed of about 19 kilometers per second. It exploded at an altitude of roughly 30 kilometers, releasing energy equivalent to approximately 500 kilotons of TNT, about 30 times the energy of the Hiroshima bomb. The airburst generated a shockwave that damaged more than 7,000 buildings and injured over 1,500 people, mostly from flying glass, and no one saw it coming. Not a single telescope, not a single survey, not a single observatory on Earth detected the Chelyabinsk asteroid before it hit. It approached from the direction of the Sun, where Earth-based telescopes cannot look, and it was too small to have been detected at any great distance, even if it had approached from a more favorable direction. Chelyabinsk was a warning shot, and it is one of the reasons the DART mission went from a theoretical concept to a funded program. Because Chelyabinsk demonstrated that asteroid impacts are not abstract hypotheticals. They are not events that happen only on geological timescales. They happen now. They happen to living people. And the next one could be larger. Didymos itself will not hit Earth. Let that be clear. The current orbital calculations, which extend centuries into the future, show no significant risk of a collision between Didymos and our planet. Didymos was chosen as the DART target precisely because it is safe, close enough to reach, hazardous enough to be a credible test case, but not actually on a collision course. The experiment was a rehearsal, not an emergency response. But the value of that rehearsal cannot be overstated, because somewhere out there, in the darkness between the planets, there is an asteroid that is on a collision course with Earth. We may not have found it yet. It may not arrive for centuries. But the laws of orbital mechanics and the cratered surfaces of every solid body in the solar system guarantee that it exists. The Moon, Mercury, Mars. Every world without a thick atmosphere to burn up incoming debris is covered in impact craters, some of them billions of years old, some of them geologically recent. Earth has been hit repeatedly throughout its history. The only reason our surface is not as cratered as the Moon's is that plate tectonics, weathering, and erosion have erased most of the evidence. The impacts happened. The craters are gone. But the asteroids are still out there. And when the next one is found, when astronomers announce that a specific asteroid, with a specific designation, is on a trajectory that will bring it within striking distance of Earth on a specific date, the first question that world leaders will ask is not, can we find it? They will already have found it. The question will be, can we stop it? The answer to that question, as of September 26, 2022, changed from we think so to we have evidence that we can. That evidence came from a tumbling pile of rubble called Dimorphos, born from the equator of its parent, Didymos, sculpted by sunlight and gravity, and struck by a machine built by human hands. But evidence is not certainty. And the gap between a successful demonstration and a reliable defense is measured not in kilometers but in the depth of our understanding. An understanding that, as the following chapters will reveal, is far more incomplete than most people realize. Understanding how deeply interconnected the two bodies of the Didymos system truly are is essential to grasping why this particular asteroid became the linchpin of humanity's planetary defense program. Didymos and Dimorphos do not simply coexist in space the way the Earth and Moon coexist. Their relationship is far more intimate and far more dynamic. The two objects orbit their common center of mass, their barycenter, at a separation of roughly 1.2 kilometers, center to center. But because Didymos is so much more massive than Dimorphos, roughly 65 times heavier, the barycenter lies well inside Didymos itself. From the perspective of an observer, Dimorphos appears to orbit Didymos, much as our Moon orbits Earth. But the physics is different in crucial ways. The gravitational field of Didymos, at the distance where Dimorphos orbits, is extraordinarily weak. The orbital velocity of Dimorphos around Didymos is only about 17 centimeters per second. That is slower than a casual walking pace. A human could outrun Dimorphos on its orbit. The escape velocity from the system, the speed at which an object would need to be launched to leave Didymos's gravitational grip entirely, is similarly tiny, on the order of tens of centimeters per second. This means that the debris ejected by the DART impact did not behave the way debris from an impact on a large planetary body would behave. Some of it escaped the system entirely. Launched at speeds exceeding the escape velocity, it flew away into heliocentric orbit, becoming its own collection of tiny asteroids. Some of it fell back to Dimorphos. Some of it may have been captured by Didymos itself. Material blasted off the moonlet's surface that drifted across the gap between the two bodies and settled onto the parent. And some of it entered chaotic orbits within the binary system, circling both bodies in complex, unpredictable paths, before eventually re-impacting one surface or the other. The debris dynamics of the DART impact within the Didymos binary system are, in many ways, more complex than the impact itself. Researchers modeling the post-impact evolution of the ejector found that the system behaved like a miniature planetary environment, complete with orbital resonances, gravitational perturbations, and accretion processes that mirror, on a tiny scale, the processes that built the planets themselves. One of the most striking findings from the post-impact observation campaign was the evolution of the debris tail. In the days following the impact, ground-based and space-based telescopes tracked the evolution of the ejector plume, as it was pushed and sculpted by solar radiation pressure. The plume initially formed a single cone of debris, expanding away from the impact site, but within days, the morphology changed. A second tail appeared, then complex filamentary structures, as different-sized particles, each responding differently to solar radiation pressure based on their size and mass, separated into distinct streams. The twin-tailed structure observed by Hubble was particularly stunning. It resembled, in miniature, the twin tails of a comet. One tail composed of dust pushed directly away from the sun by radiation pressure, and the other composed of larger particles following a slightly different trajectory due to their greater inertia. Dimorphos, for a brief period, had become a comet of sorts, not because it was outgassing volatiles, the way true comets do, but because the impact had created an artificial cloud of debris that behaved like cometary dust. This was more than a visual spectacle. The structure and evolution of the debris tails provided critical data about the size distribution and velocity distribution of the ejected material. By modeling how the tails evolved over time, researchers could work backward to estimate how much total mass was ejected, at what speeds, and in what directions. These parameters, in turn, constrained the momentum enhancement factor, beta, and provided insights into the mechanical properties of Dimorphos's surface. The picture that emerged was consistent across multiple independent analyses. Dimorphos's surface is composed primarily of boulders and cobbles with relatively little fine-grained material. The impact excavated material from a depth of several meters, possibly deeper. The ejection velocities ranged from less than 1 meter per second to several hundred meters per second, with the bulk of the ejected mass traveling at relatively low speeds, consistent with a loosely bound rubble pile surface where the energy of the impact was efficiently coupled to the surrounding material. But here is what makes this truly terrifying. The very properties that made DART so effective at Dimorphos, the loose structure, the efficient momentum transfer, the copious ejector, are the same properties that make rubble pile asteroids the most unpredictable targets for planetary defense. Each rubble pile is different. Each has a unique internal structure, a unique size distribution of constituent boulders, a unique porosity, a unique cohesion. There is no guarantee that the next asteroid humanity needs to deflect will respond the same way Dimorphos did. The beta value of 3.6 is one data point. 1. Extrapolating from a single experiment to a general strategy for planetary defense is like testing one vaccine on one patient and declaring the pandemic solved. This is why HERA matters. This is why continued investment in asteroid science matters. This is why the story of Didymos, far from being complete, is only entering its most critical phase. The first act, discovery, is done. The second act, the impact, is done. The third act, understanding what the impact actually did and what it means for the future, has only just begun. The DART impact was not an isolated event. It was the culmination of decades of theoretical work, failed proposals, competing visions, and hard-won incremental progress. To understand what the impact on Dimorphos truly means, you have to understand the long, tortuous road that led to it. A road paved with ambition, skepticism, political compromise, and the kind of stubborn persistence that only scientists facing an existential threat can sustain. The first serious proposals for asteroid deflection emerged in the 1960s, in the shadow of the Cold War. The nuclear powers possessed weapons of extraordinary destructive force, and it did not take long for someone to ask, could those weapons be used for something constructive? Could a nuclear detonation be used to push an asteroid off a collision course with Earth? The idea was explored in a series of classified and semi-classified studies, primarily in the United States and the Soviet Union. The physics was straightforward in principle. A nuclear weapon detonated near the surface of an asteroid would vaporize a thin layer of rock on the surface closest to the blast. That vaporized rock would expand outward in a violent jet, and the reaction force, Newton's third law, once again, would push the asteroid in the opposite direction. The deflection would depend on the yield of the weapon, the distance of the detonation, and the composition and size of the asteroid. On paper, nuclear deflection was the most powerful tool available. A single large thermonuclear weapon could, in theory, impart enough momentum to deflect even a kilometer-scale asteroid, provided the detonation was performed far enough in advance. But the practical obstacles were enormous. First, there was the political dimension. The Outer Space Treaty of 1967 prohibits the placement of nuclear weapons in orbit and bans nuclear explosions in space. While the treaty does not explicitly address the use of nuclear weapons for planetary defense, a scenario not envisioned by its framers, the political sensitivity of proposing to send nuclear weapons into space was, and remains, immense. Any nation that attempted to launch a nuclear-armed deflection mission would face intense scrutiny, suspicion, and potential opposition from other nations. Second, there was the scientific uncertainty. The nuclear deflection models assumed that the asteroid was a solid body, a coherent mass that would absorb the energy from the blast and respond with a clean, predictable push. But as the rubble pile model gained acceptance in the 1990s and 2000s, the limitations of nuclear deflection became clearer. A nuclear blast near a loosely bound rubble pile might not push the asteroid at all. It might shatter it. Instead of one object on a collision course, you might create dozens or hundreds of fragments, many of which could still be on Earth-impacting trajectories. A shotgun blast of debris, as the metaphor goes, is harder to dodge than a single bullet. Third, there was the testing problem. Nuclear deflection has never been tested on an actual asteroid. The physics is modeled, simulated, and debated, but it has never been verified by experiment. And given the political and environmental constraints on nuclear testing, it is unlikely to be tested anytime soon. This means that if humanity ever needs to resort to nuclear deflection, it will be doing so for the first time under the most stressful conditions imaginable, with no empirical data to validate the predictions. Despite these concerns, nuclear deflection has not been abandoned. It remains, in the view of many planetary defense experts, the only viable option for deflecting very large asteroids, those above roughly 1 kilometer, or for deflecting smaller asteroids with very short warning times, where a kinetic impactor would not have enough lead time to achieve a sufficient deflection. The nuclear option is the last resort, the ace in the hole, the strategy that nobody wants to use but nobody can afford to discard. But for the vast majority of scenarios, asteroids smaller than 1 kilometer, with warning times of years or decades, the kinetic impactor approach demonstrated by DART is the preferred strategy. And the path to DART was shaped by a series of earlier missions and proposals, each of which contributed a piece of the puzzle. The first mission to visit a near-Earth asteroid was Near Shoemaker, launched by NASA in 1996. The same year Didymos was discovered. Near Shoemaker was sent to the asteroid 433 Eros, one of the largest near-Earth asteroids, roughly 34 kilometers long and approximately 13 kilometers wide. The spacecraft entered orbit around Eros in February of 2000 and spent a year mapping the surface in extraordinary detail before making a controlled descent to the surface on February 12, 2001. Eros was not a rubble pile, it was a fractured monolith, a single coherent body, cracked and scarred by billions of years of impacts, but fundamentally solid. Its density was approximately 2.67 grams per cubic centimeter, close to the density of the silicate minerals that composed it, indicating very little internal void space. The surface was covered in craters, boulders, and a layer of fine regolith called a dust pond in the low-gravity depressions. Near Shoemaker taught scientists what a solid near-Earth asteroid looked like, but it also raised a question. Was Eros typical, or was it the exception? The answer, as subsequent missions would reveal, was that Eros was very much the exception. Most near-Earth asteroids, particularly the smaller ones, turned out to be rubble piles, loose aggregates with dramatically different properties. The mission that most dramatically changed the understanding of asteroid structure was the Japanese Aerospace Exploration Agency's Hayabusa, launched in 2003. Hayabusa's target was the asteroid 25,143 Itokawa, a tiny body roughly 535 meters long and roughly 210 meters wide. Itokawa was named after Hideo Itokawa, the father of Japanese rocketry, and it became the first asteroid from which a sample was returned to Earth. When Hayabusa arrived at Itokawa in September of 2005, the images it returned were startling. Itokawa looked nothing like Eros. Where Eros was a solid, cratered body with a clear geological history, Itokawa was a peanut-shaped jumble of boulders and gravel. Its surface showed two dramatically different terrains: rough, boulder-strewn highlands and smooth, gravel-filled lowlands called the Muses Sea. The lack of significant craters, the segregation of boulders by size, and the extremely low density, roughly 1.9 grams per cubic centimeter, far below the density of its constituent minerals, all pointed to the same conclusion. Itokawa was a rubble pile, a collection of fragments from some ancient catastrophic collision, reassembled by gravity into a single body, held together by nothing more than its own feeble gravitational pull. Hayabusa's sample return mission was a drama in its own right. The spacecraft suffered multiple failures. Its reaction wheels failed, chemical thrusters sprang leaks, communications were lost for months, and the sample collection mechanism did not function as designed. When Hayabusa finally returned to Earth in June of 2010, crash landing its sample capsule in the Australian outback, the recovery team did not know whether any asteroid material had actually been captured. It had. Tiny grains of Itokawa, less than a milligram in total, were found inside the capsule. Those grains confirmed that Itokawa was an ordinary chondrite, composed of the same silicate minerals found in the most common type of meteorite. But the grains also revealed something unexpected. They showed signs of space weathering, the slow darkening and chemical alteration caused by exposure to solar wind and micrometeorite bombardment. The surface of Itokawa was ancient and battered, but the body itself was young, assembled from the debris of an older, larger asteroid that had been destroyed perhaps in the last few 100 million years. Itokawa was the first clear, close-up portrait of a rubble pile asteroid, and it raised the stakes for planetary defense enormously. If most near-Earth asteroids are like Itokawa, loose, fragile, barely bound, then deflecting them requires a fundamentally different approach than deflecting a solid body like Eros. You cannot simply push a rubble pile the way you push a brick. You have to understand how the push will propagate through a structure with no tensile strength, no cohesion, no mechanical integrity. The next major chapter in the story came from two missions that arrived at their targets almost simultaneously. In late 2018, NASA's OSIRIS-REx spacecraft reached the asteroid 1955 Bennu on December 3, 2018. Less than 4 months earlier, in June 2018, JAXA's Hayabusa 2 had arrived at the asteroid 162,173 Ryugu. Both missions were designed to study their targets in detail and return samples to Earth. Both delivered results that reshaped the understanding of rubble pile asteroids. Ryugu and Bennu are remarkably similar in many ways. Both are roughly 500 meters across. Both are shaped like spinning tops, oblate spheroids with pronounced equatorial ridges, the signature shape of a rubble pile that has been spun up by the Yorp. Both are classified as carbonaceous asteroids, rich in carbon, organic molecules, and hydrated minerals. Both are extremely dark, reflecting only about 4 to 5% of the sunlight that hits them. And both are covered in boulders. The boulder coverage was the first surprise. Pre-arrival models had predicted that both asteroids would have significant areas of smooth, fine-grained regolith, material that had been ground down by impacts over billions of years. Instead, both surfaces were dominated by boulders, some as large as houses, with very little fine material in between. This was a problem for both missions, since their sample collection mechanisms had been designed to scoop up fine regolith, not to chip off pieces of boulders. Both teams had to improvise. Hayabusa 2 took an even more dramatic step. In April of 2019, it deployed a small copper projectile called the Small Carry-On Impactor, or SCI, at the surface of Ryugu. The projectile struck at roughly 2 kilometers per second, creating an artificial crater approximately 14.5 meters in diameter. This was, in effect, a small-scale kinetic impact test, the first ever conducted on an asteroid's surface. The crater provided a window into Ryugu's subsurface, revealing that the material just below the surface, was similar in composition to the surface itself, but slightly brighter, less space-weathered. It also showed that the surface was mechanically weak. The projectile penetrated easily, creating a crater larger than predicted for a cohesive surface. The Hayabusa 2 impact on Ryugu was a direct precursor to DART. It demonstrated that a kinetic impact on a rubble pile asteroid could excavate significant amounts of material. It provided data on the cratering mechanics of a loosely bound surface, and it gave the DART mission team a real-world benchmark against which to calibrate their models. But the Hayabusa 2 impactor was small, just 2.5 kilograms, and it struck at a relatively low speed. DART would be orders of magnitude more energetic. Scaling from Ryugu's small crater to DART's full-scale impact required extrapolation across a vast range of impact energies, and the uncertainty in that extrapolation was one of the central anxieties of the DART mission. OSIRIS-REx, meanwhile, contributed a different piece of the puzzles. During its close approach to Bennu's surface for the sample collection maneuver, the Touch and Go, or TAG, event on October 20, 2020, the spacecraft sampling arm penetrated the surface far more deeply than expected. The surface of Bennu offered almost no resistance. The sampling head sank roughly half a meter into the regolith before the spacecraft fired its thrusters to back away. Later analysis revealed that Bennu's surface has the consistency of a ball pit, a thin crust of interlocking particles over a void-rich interior with almost no cohesion. The implications were staggering. If the surface of a rubble pile asteroid is this weak, this porous, this structureless, then a kinetic impactor might behave very differently than expected. It might bury itself before transferring its momentum to the bulk of the asteroid. It might compact the surface without excavating much material. It might even pass through a region of low density without encountering enough mass to stop it. The physics of the interaction depends critically on the exact structure of the surface layers that cannot be characterized from Earth and that, until Hera arrives at Dimorphos, have never been studied in detail at a DART-impacted surface. And this is where the competing theories enter the picture. In the years leading up to the DART mission, several research groups developed independent models of how the impact would unfold. These models differed in their assumptions about Dimorphos' structure, and they produced dramatically different predictions. One school of thought, based on smooth particle hydrodynamic simulations, a computational technique that models solid bodies as collections of interacting particles, predicted a relatively conventional cratering event. The impactor would strike the surface, excavate a bowl-shaped crater a few tens of meters across, and eject material in a cone-shaped plume. The momentum enhancement factor would be modest, perhaps 1.5 to 2.5. The change in Dimorphos' orbital period would be measurable but small, perhaps 7 to 10 minutes. A second school of thought, based on discrete element models, simulations that treat the rubble pile as individual boulders interacting through contact forces and gravity, predicted a very different outcome. In these simulations, the impactor did not merely crater the surface, it sent shock waves through the loose interior of the rubble pile, mobilizing material far from the impact site. The resulting ejector plume was much larger, much more massive, and the momentum enhancement factor was correspondingly higher, potentially 3 to 5 or even higher. A third perspective, advanced by researchers who emphasized the role of target porosity, predicted that the impactor might simply bury itself in a highly porous surface, with minimal ejector and a beta close to 1. This was the worst-case scenario for planetary defense, an impact that barely moves the asteroid at all. The math is striking when you compare these predictions side by side. One model said Dimorphos' orbit would change by 7 minutes, another said 30 minutes, another said 2 minutes. The range of predictions spanned more than an order of magnitude, and each prediction was based on reasonable assumptions, supported by credible physics, published in peer-reviewed journals by respected researchers. The disagreement was not sloppy science. It was the honest reflection of profound uncertainty about the mechanical properties of a body that had never been touched by human technology. When the actual result came in, 32 minutes, it vindicated the discrete element models and exceeded even some of the most optimistic predictions. The beta of 3.6 Place the dart impact squarely in the regime where ejector momentum dominated the deflection. The pessimistic models were wrong. The optimistic models were approximately right. And the conservative models, the ones that many mission planners had used as their baseline, had significantly underestimated the effectiveness of the kinetic impactor. This was, in one sense, wonderful news. It meant that kinetic deflection was more effective than the cautious estimates had suggested. But it also meant that the cautious estimates, the ones used to design future missions, to calculate required spacecraft masses, to determine launch windows, to plan multi-year deflection campaigns, were significantly miscalibrated. The planetary defense community had been designing missions based on assumptions that were too pessimistic, which sounds like good news until you realize what it implies. The models are wrong, not catastrophically wrong, not useless, but wrong enough that relying on them for a real deflection campaign, where lives depend on the accuracy of the prediction, would be deeply dangerous. And here the story of Didymos connects to something much larger, the fundamental problem of prediction in a universe that does not read our textbooks. Every model is a simplification, every simulation makes assumptions, and when the object you are trying to model is a collection of irregularly shaped boulders, loosely bound by the weakest gravitational field imaginable, orbiting another equally chaotic body under the influence of forces as subtle as sunlight, the gap between model and reality can be vast. The European Space Agency's Hera mission is designed to close that gap. Launched on October 7, 2024, aboard a SpaceX Falcon 9, Hera is a spacecraft roughly the size of a desk, equipped with a suite of instruments far more capable than DART's single camera. Its primary mission is to return to the Didymos system and conduct a detailed survey of both bodies, with particular attention to the impact crater on Dimorphos and the changes wrought by the DART collision. Hera carries two small CubeSats, Milani and Juventus, that will be deployed near the Didymos system. Milani will study the surface composition of both asteroids using a multispectral imager and a dust detector. Juventus will probe the interior structure of Dimorphos using a low-frequency radar, the first time a rubble pile asteroid's interior has been directly measured. Together, the three spacecraft will provide a comprehensive portrait of the post-impact Didymos system that will transform the understanding of how kinetic impacts affect rubble pile bodies. But Hera is not merely a follow-up mission. It is a scientific necessity. Without the data that Hera will provide, the DART result is a number without context. A beta of 3.6 tells you what happened at Dimorphos. It does not tell you why. It does not tell you whether the same result would occur at a different rubble pile with a different porosity, a different boulder size distribution, a different thermal history. It does not tell you whether the impact created a simple bowl-shaped crater or a complex, irregular excavation. It does not tell you how much mass Dimorphos lost, or whether its shape changed, or whether its spin state was altered. All of these details matter enormously for planetary defense. If the DART impact created a specific type of crater in a specific type of rubble pile, and Hera can characterize both the crater and the rubble pile, then modelers will have the data they need to calibrate their simulations. Future predictions will be grounded in observation, not assumption. The gap between model and reality will narrow, and the next time humanity faces a real asteroid threat, not a test, not a drill, but a genuine emergency, the deflection strategy will be based on demonstrated physics, not educated guesses. There is another exploration thread that deserves attention, one that is less well known but equally important. In parallel with the DART program, a community of researchers has been studying the problem of asteroid deflection from a completely different angle: gravity tractors. The gravity tractor concept, first proposed by astronauts Edward Lu and Stanley Love in 2005, is as elegant as it is counterintuitive. Instead of hitting an asteroid, you park a spacecraft next to it. The spacecraft hovers near the asteroid for months or years, maintaining a fixed distance using its thrusters. The gravitational attraction between the spacecraft and the asteroid, tiny but real, exerts a continuous pull on the asteroid, slowly altering its trajectory. Over time, the cumulative deflection can be significant. The beauty of the gravity tractor is that it requires no physical contact with the asteroid. It does not depend on the asteroid's composition, structure, or surface properties. It works equally well on solid monoliths and rubble piles. It does not risk shattering a fragile body. And because the deflection is gradual and continuous, it can be precisely monitored and adjusted in real time. The drawback is time. A gravity tractor requires years, possibly decades, to achieve a meaningful deflection. This means it is only viable if the asteroid is discovered far in advance of its projected impact, a best-case scenario that is not guaranteed. For short warning time scenarios, the gravity tractor is too slow, but for long warning time scenarios, it may be the safest and most reliable option available. No gravity tractor mission has ever been flown. The concept remains theoretical, but it represents an important alternative to kinetic impact, and the interplay between the two approaches, fast but uncertain kinetic impact versus slow but reliable gravitational deflection, is one of the central debates in planetary defense planning. A third approach, still in the early stages of research, involves ion beam deflection. In this concept, a spacecraft equipped with an ion engine parks near the asteroid and aims its ion beam at the asteroid's surface. The beam exerts a tiny but continuous force on the asteroid, gradually pushing it onto a different trajectory. Like the gravity tractor, ion beam deflection is slow and requires long lead times, but it has a potential advantage. The force exerted by the ion beam can be much greater than the gravitational attraction of the spacecraft alone, potentially reducing the required deflection time. Each of these approaches, nuclear detonation, kinetic impact, gravity tractor, ion beam, has strengths and weaknesses. Each is suited to different scenarios, and none of them has been fully tested. DART provided the first empirical data point for kinetic impact. No equivalent experiment has been conducted for any of the other methods. The Planetary Defense Toolkit is still largely theoretical, with one demonstrated tool and several promising concepts. The Didymos system sits at the center of this landscape. It is the laboratory where the first tool was tested. It is the benchmark against which all future predictions will be measured, and it is, in a very real sense, the birthplace of practical planetary defense. Before Didymos, planetary defense was a theory. After Didymos, it is a measured capability, incomplete, imperfect, but real. But the limitations of that single measurement must not be forgotten. DART struck one asteroid, of one size, of one composition, at one speed, at one angle. The universe contains millions of near-Earth objects, each with its own unique properties. Extrapolating from one experiment to a general defense strategy is like testing one antibiotic against one bacterial strain and declaring all infections curable. The science is promising, the result is encouraging, but the work, the hard, expensive, time-consuming work of building a comprehensive understanding of how asteroids respond to human intervention has barely begun. There is one more chapter in the exploration of Didymos that deserves to be told, and it is perhaps the most dramatic of all. It is the story of the last 4 hours of DART's existence, when the spacecraft transitioned from a navigated vehicle, underground control, to a fully autonomous machine, making its own decisions in the darkness between planets. The challenge of hitting Dimorphos was not merely one of aiming, it was one of seeing. From Earth's perspective, Dimorphos was invisible. Ground-based telescopes could see the combined light of the Didymos system. The two bodies blurred together into a single point, but they could not resolve the individual objects. Even the most powerful planetary radar could distinguish between Didymos and Dimorphos only as patterns in the returned signal, not as visible images. DART's camera, Draco, was the only eye that could see the target directly, and Draco could not resolve Dimorphos as a separate object until the spacecraft was very close. The SmartNav system, small body maneuvering, autonomous real-time navigation, was the critical technology that made the impact possible. SmartNav was an onboard software system that analyzed Draco images in real time, identified Didymos and Dimorphos as they became resolvable, determined which was the target, and commanded the spacecraft's thrusters to steer toward impact. It was, in effect, the world's first autonomous asteroid targeting system. The timeline of the final approach was compressed and intense. At roughly 4 hours before impact, SmartNav took over navigation. At that point, Dimorphos was still not visible as a separate object. It was lost in the glare of the larger Didymos. SmartNav initially targeted Didymos itself, using it as a reference point, knowing that as the spacecraft closed the distance, Dimorphos would eventually separate from its parent in the images. At roughly 1 hour before impact, Dimorphos became visible for the first time, a tiny speck of light adjacent to the larger, brighter Didymos. SmartNav identified it, locked onto it, and began steering the spacecraft away from Didymos and toward the moonlet. From this point forward, every image was a revelation. Each frame showed Dimorphos slightly larger, slightly more detailed than the last up. Surface features emerged. The outline of the body became clear. Individual boulders appeared. The images streamed back to Earth in near real time, with a delay of roughly 38 seconds each way. The mission control team at Johns Hopkins Applied Physics Laboratory watched as Dimorphos grew from a dot to a disk to a world. They could not intervene. They could not adjust the course. They could only watch. In the final 2 minutes, the images came in at a rate of 1 per second. Dimorphos filled more and more of the frame. The surface details were astonishing. A chaotic landscape of angular boulders, some bright, some dark, casting sharp shadows in the low sun angle. There was no smooth regolith, no dust plains, no gentle terrain, just rocks. Rocks piled on rocks, balanced on rocks, scattered across a surface so rough that it defied the neat, smooth ellipsoid that the pre-mission models had imagined. The last complete image from DART, captured roughly 2 seconds before impact, showed a patch of surface approximately 31 meters across. Individual boulders 1 to 2 meters in size were clearly visible. The image was crisp, detailed, and utterly alien, a close-up of a world that no human eye had ever seen, captured by a machine in the last heartbeat of its existence. Then the signal stopped. The screen in mission control went red. DART was gone. The room erupted. Engineers and scientists who had spent years, in some cases more than a decade, working toward this moment embraced, cheered, and wept. Laurie Glaze, the director of NASA's Planetary Science Division, called it a new era for humankind. Andy Rivkin, the DART investigation team lead, later reflected on the strangeness of celebrating the deliberate destruction of a spacecraft you had spent years building. "We designed it to be destroyed," he said, "and it performed exactly as designed. But watching it happen, watching the signal die, was still a gut punch." The LysiaCube images, captured by the tiny Italian CubeSat that had been released from DART 15 days before the impact, provided a different perspective. LysiaCube flew past Dimorphos approximately 3 minutes after the DART impact, capturing images of the ejector plume from a vantage point that DART's camera could never have achieved. The images showed a massive cone of debris erupting from the impact site, bright against the black sky, expanding outward in a ragged, asymmetric plume. The ejector was not uniform. It showed structure, rays, clumps, streamers, consistent with a surface composed of discrete boulders and fragments rather than a homogeneous material. These images, combined with the ground-based and space-based telescope observations that continued for weeks after the impact, provided the most comprehensive dataset ever collected on an asteroid impact event. They were the raw material from which the beta measurement was derived. They were the evidence that planetary defense had entered a new era, and they were, in a quiet but profound way, the most important photographs ever taken, because they showed that humanity could reach out across the void and touch the trajectory of another world. But they also showed something less comfortable. The images revealed that Dimorphos was more complex, more chaotic, and more poorly understood than the models had assumed. The pre-impact shape models, based on radar and light curve data, had predicted a relatively smooth, elongated ellipsoid. The reality was far more irregular, a lumpy, asymmetric body that bore little resemblance to the idealized shapes used in the simulations. This discrepancy between prediction and reality is not a failure of science. It is a reminder that every model is a map, and no map is the territory. The territory, in this case, is a pile of ancient rubble hurtling through the cosmos at roughly 23 kilometers per second relative to the Sun, carrying within its structure the frozen memory of 4.6 billion years of collision, accretion, disruption, and reassembly. Dimorphos is not merely an object, it is an archive. Its boulders were once part of a larger body. That larger body was once part of a planetesimal. That planetesimal was once a cloud of dust grains swirling around a newborn star. Every rock on Dimorphos' surface has a history that stretches back to the birth of the solar system itself. And now, layered atop that ancient history, there is a new chapter, a crater, a plume, a changed orbit, written by a civilization that has existed for the merest fraction of Dimorphos' lifetime. A civilization that, for the first time, is not merely observing the cosmos, but intervening in it. There is one more thread in this story, Sant, that ties the explorations together. The question of what the DART impact revealed about how binary asteroid systems form and evolve. Before DART, the prevailing model held that Dimorphos formed through Yorp-driven mass shedding from Didymos. The material spun off the equator, entered orbit, and gradually accreted into a single moonlet. This model predicted that Dimorphos would be composed of relatively fine-grained material, the loose regolith and small fragments that would be most easily dislodged by centrifugal force. The DART images shattered that prediction. Dimorphos' surface was dominated by large boulders, some several meters across. These boulders were too large to have been lofted off Didymos' equator by the Yorp spin-up process alone. Their presence suggested that the formation of Dimorphos was more violent, more energetic, and more complex than the gentle mass shedding model had assumed. One possibility is that Dimorphos formed from a catastrophic disruption event, a large impact on Didymos that blasted significant quantities of material into orbit, where it subsequently reassembled. Another possibility is that the Yorp process was punctuated by episodes of rapid mass loss, rotational fission events in which large chunks of Didymos broke away at once, rather than a steady trickle of fine material. A third possibility is that Dimorphos' large boulders are not primordial. They were produced by subsequent impacts on the moonlet surface after it formed, shattering the original fine-grained material and replacing it with larger fragments. Each of these scenarios has different implications for planetary defense. If Dimorphos formed from fine material and was subsequently resurfaced by impacts, then its interior might be very different from its surface, potentially more porous, more compressible, and less responsive to kinetic deflection than the surface boulders would suggest. If it formed from large fragments, then its interior might be more coherent, a collection of interlocking boulders with significant friction between them, potentially making it more responsive to deflection. The relationship between surface appearance and interior structure is one of the great unknowns of asteroid science, and it is one of the primary questions that Hera's radar instrument, carried by the Juventus CubeSat, is designed to address. The Didymos system also raised intriguing questions about the long-term stability of binary asteroids. The gravitational interaction between Didymos and Dimorphos is not static. Tidal forces, the same kind of forces that cause ocean tides on Earth, and that are gradually slowing Earth's rotation while pushing the Moon farther away, are at work in the Didymos system as well. Over millions of years, these tidal interactions transfer energy between the spin of the two bodies and their mutual orbit, gradually changing the system's configuration. In some binary asteroid systems, tidal evolution drives the secondary outward, eventually causing it to escape the primary's gravitational influence. In others, tidal forces drive the secondary inward, eventually causing it to crash into the primary, or to be torn apart by tidal stresses when it crosses inside the Roche limit, the distance within which the primary's tidal forces exceed the secondary's own gravity. The fate of Dimorphos over astronomical timescales is still uncertain. It may be a permanent companion of Didymos, stabilized by some equilibrium between tidal dissipation and Yorp-driven spin changes, or it may be a temporary feature, a moon that will one day spiral inward and be reabsorbed by its parent, or drift outward and escape, becoming an independent asteroid. This uncertainty is more than academic curiosity. It bears directly on the question of how common binary asteroid systems are, how long they persist, and how many of the solitary asteroids we observe today were once members of binary systems that have since dissolved. If binary formation and dissolution is a common process among small asteroids, then the population of near-Earth objects is more dynamic, more complex, and more difficult to characterize than a simple census of individual bodies would suggest. The story of Didymos is, ultimately, a story about the limits of knowledge. Every answer generates new questions. Every measurement reveals new uncertainties. Every successful mission exposes the gaps in our understanding that the next mission must address. This is not a weakness of science. It is its greatest strength. The willingness to confront uncertainty, to acknowledge ignorance, to design experiments that test our assumptions rather than confirm our biases. This is what makes science the most powerful tool humanity has ever developed for navigating a universe that was not designed for our convenience. And Didymos, the twin, the parent of Dimorphos, the target of DART, the laboratory of planetary defense, sits at the center of this ongoing investigation, a silent, tumbling monument to everything we have learned and everything we have yet to discover. There is a moment in every deep investigation where the facts stop being merely informative and start being unsettling, not because they are wrong, not because they contradict each other, but because, taken together, they paint a picture that is larger and stranger than any single fact could convey. The story of Didymos reaches that moment here. Consider what we now know. The solar system is littered with debris, hundreds of thousands of rocky fragments orbiting the sun, ranging in size from grains of dust to objects hundreds of kilometers across. A significant fraction of these objects occupy orbits that cross the paths of the inner planets, including Earth. The vast majority of near-Earth objects in the most dangerous size range, 140 meters and above, have not been discovered. Those that have been studied up close turn out to be rubble piles, loosely bound collections of boulders and gravel, held together by gravity so weak that an astronaut could escape their surfaces by jumping. The one experiment humanity has conducted on deflecting such an object produced a result that exceeded most predictions, suggesting that kinetic impactors are more effective than feared, but also confirming that the models used to predict outcomes are imprecise. Now step back. Look at the whole picture. We live on a planet that has been struck by asteroids throughout its history. The impacts have caused mass extinctions, reshaped continents, and altered the trajectory of life on Earth. The objects that pose the greatest threat in our current era are, by and large, rubble piles, fragile, chaotic, poorly understood bodies that we have only begun to study up close. Our one attempt to deflect such a body worked better than expected, but we do not fully understand why. And the follow-up mission that will provide the critical data needed to understand the result has not yet arrived at its destination. This is not science fiction. This is the actual state of planetary defense as of the mid-2020s. Let that sink in. Humanity's ability to protect itself from asteroid impacts rests on a foundation of knowledge that is remarkably thin. We have discovered most of the largest near-Earth asteroids. We have characterized a handful of them up close. We have struck one of them once and measured the result. That is the entirety of our empirical foundation. Everything else is theory, simulation, and extrapolation. The philosophical weight of this realization is difficult to overstate. For the first time in the history of life on Earth, a species has developed the awareness to recognize the threat of asteroid impacts and the technology to potentially do something about it. No dinosaur saw the Chicxulub impactor coming. No trilobite understood the late heavy bombardment that reshaped the surfaces of the inner planets 4 billion years ago. We are the first species in the 4.5 billion year history of this planet to look up at the sky and know, truly know, with mathematical precision, that rocks from space have ended worlds before and will try to end them again. And yet, our response to this knowledge has been measured in the millions of dollars, not billions. The DART mission cost approximately $330 million. That is roughly the cost of a single advanced fighter jet. The annual budget for NASA's planetary defense program is a fraction of a percent of the agency's total budget. The global investment in finding and tracking near-Earth asteroids amounts to less than a large city spends on its road maintenance. There is a cognitive dissonance at work here. We know the threat is real. We know the consequences of a significant impact would be catastrophic. We have the technology to detect threatening objects and, in some cases, to deflect them. And yet, as a civilization, we have invested less in this existential risk than we spend on streaming entertainment in a single quarter. This is not an indictment of any individual or institution. It is a reflection of how human beings process risk. We are wired by evolution to respond to immediate, visible threats. A predator in the bushes, a storm on the horizon, an enemy at the gates. We are profoundly bad at responding to threats that are statistically certain but temporally remote. Threats that might materialize in a decade, a century, or a millennium. An asteroid impact is the ultimate example of such a threat. It will happen. We do not know when. And because we do not know when, we struggle to act as if it matters. Didymos and the DART mission represent a crack in that complacency. For the first time, a government agency invested real money, real engineering talent, and real political capital in a mission whose sole purpose was to prepare for an asteroid impact that might not happen for centuries. That is an extraordinary act of foresight. It is the kind of long-term thinking that civilizations are remembered for, or, in the absence of which, are not remembered at all. But here is the deeper truth. The DART mission did not merely demonstrate that kinetic deflection works. It demonstrated something more fundamental. That the universe is not indifferent to our survival, but it is indifferent to our awareness. The asteroids do not care whether we know about them. They do not care whether we have telescopes or spacecraft or contingency plans. They follow their orbits with the blind mechanical precision of gravity and inertia. And if one of those orbits intersects Earth's at the wrong time, the result will be the same whether we are watching or not. What DART changed is not the physics of asteroids. It changed the physics of us. It moved humanity from a species that could only observe and worry to a species that could observe, worry, and act. That transition, from passive awareness to active capability, may be the single most important step our species has taken since the invention of agriculture. Because agriculture allowed us to survive as a civilization. Planetary defense allows us to survive as a species. And yet, the capability is fragile. It depends on continued investment, continued vigilance, continued scientific investigation. If the telescopes go dark, if the budgets are cut, if the political will evaporates, then the capability dies. And we are back to where we were before DART, watching the sky and hoping. Let that sink in. There is a particular kind of loneliness that comes with understanding the place of Earth in the cosmos. Not the loneliness of isolation, though we are, as far as we know, alone in this region of the galaxy, but the loneliness of vulnerability. Earth is a thin shell of rock and water wrapped around a ball of molten iron, spinning in the void, protected from the radiation of space by a magnetic field so tenuous it could be disrupted by a sufficiently powerful solar flare. Our atmosphere is a gossamer layer, thinner in proportion to the planet's diameter than the skin of an apple. And this fragile world, this improbable sanctuary of warmth and water and breathable air, orbits in a cosmic shooting gallery, surrounded by millions of rocky projectiles, any one of which could, given the right trajectory and enough time, bring everything to an end. Every atom in your body was forged inside a dying star. The calcium in your bones, the iron in your blood, the oxygen you are breathing right now, all of it was manufactured in the nuclear furnaces of stars that exploded billions of years ago, scattering their enriched material across the galaxy. That material coalesced into a new solar system, a new planet, a new biosphere, and some of it coalesced into asteroids. The same stellar forge that made you also made Didymos. You and the asteroid that might someday threaten your world share a common origin. You are made of the same stuff. There is something both beautiful and terrifying about that connection. The universe created the conditions for life and the conditions for the destruction of life from the same raw materials, through the same processes, in the same event. Creation and destruction are not opposites in the cosmos. They are aspects of the same process, the endless cycling of matter and energy through forms, some of which are conscious and most of which are not. Didymos does not know it was struck by a human spacecraft. It does not know it has been named, studied, debated, and feared. It is a collection of ancient rock, spinning in the void, following an orbit that has barely changed in millions of years. It is indifferent to us. And that indifference is, in its own way, the most terrifying thing about it, because indifference is not malice. You can reason with malice. You cannot reason with a rock. The scientists who designed the DART mission understood this. They understood that you cannot negotiate with an asteroid. You cannot deter it. You cannot frighten it. You can only push it. And to push it effectively, you must understand it. Its structure, its composition, its response to force, its orbital dynamics. The DART mission was not a show of strength. It was an act of understanding. An acknowledgement that survival in this universe requires not just courage or ingenuity, but humility. The humility to study what you fear, to measure what you cannot see, to prepare for what may never happen in your lifetime, but will certainly happen in someone's. The Didymos system will continue to orbit the Sun for millions of years. Dimorphos will continue to orbit Didymos, its period shortened by 32 minutes, its surface altered by the first intentional human impact on another world. Hera will arrive and study the aftermath, providing data that will inform the next generation of planetary defense strategies. New telescopes, like the Vera C. Rubin Observatory in Chi, which will begin surveying the sky in the mid-2020s, will discover thousands of previously unknown near-Earth objects, adding to the catalogue and reducing the number of unseen threats. But the fundamental situation will not change. Earth is, and will always be, a target. The question is not whether another significant asteroid impact will occur. It is whether, when it does, humanity will be ready. The DART mission was the first step toward readiness. The story of Didymos is the story of that first step, tentative, imperfect, but real. And beneath all the data, all the measurements, all the orbital mechanics and momentum transfer calculations, there is a simpler truth. We are a species that looked up at the sky, saw what was coming, and chose to do something about it. That choice, that defiant, improbable, beautiful choice, is what separates us from every other species that has ever lived on this planet. The dinosaurs could not choose. We can, and we did. Whether we continue to choose wisely, whether we invest in detection, research, and readiness, will determine whether our civilization endures for centuries or millennia, or whether it becomes another layer of sediment in the geological record, a thin stratum of ash and iridium, marking the moment when a species that could have saved itself chose not to. There is a thought experiment that planetary defense scientists sometimes use to illustrate the stakes. Imagine that you are standing on a beach, watching the ocean. You know intellectually that tsunamis exist. You know that somewhere out there, beneath the surface of the sea, a fault line could slip, or a landslide could collapse, and a wall of water could race toward you at hundreds of kilometers per hour. You know that tsunamis have killed hundreds of thousands of people throughout history. And yet, as you stand there watching the calm, blue water, the threat feels abstract, distant, unlikely. Now imagine that you are standing on the same beach, but this time you have a seismograph. You can see the vibrations in the earth. You can measure the movement of tectonic plates. You know, not just intellectually but empirically, that a tsunami is possible, and you have some ability to predict when one might occur. You are no longer ignorant. You are aware. And with that awareness comes a responsibility that did not exist before. That is where humanity stands right now with respect to asteroid impacts. We are no longer ignorant. We can see the rocks. We can measure their orbits. We can calculate the probabilities. And we have demonstrated with DART that we have at least a rudimentary ability to intervene. The question is whether we will act on that awareness, whether we will build the early warning systems, fund the deflection programs, and create the international frameworks needed to respond effectively, or whether we will stand on the beach, watching the calm sky, and hope that the wave never comes. The geological record is unambiguous. The wave always comes. The only question is when, and whether anyone will be prepared. There is a concept in risk analysis called the survivor's paradox. Every civilization that has survived to the present day is, by definition, one that has not yet been destroyed by a catastrophic event. But the absence of destruction in the past does not guarantee its absence in the future. It simply means that, so far, the dice have rolled in our favor. The asteroid that killed the dinosaurs rolled against them. The near misses that have grazed Earth's atmosphere, Chelyabinsk, Tunguska, the undetected objects that have flown between Earth and the Moon, without our knowledge, have rolled in our favor. But the dice do not have memory. Each role is independent, and the longer we wait without experiencing a significant impact, the more complacent we become, even as the probability of an impact, over long timescales, approaches certainty. Didymos is the antidote to that complacency, not because it is dangerous, but because it is instructive. It taught us what rubble pile asteroids look like. It taught us how they respond to impacts. It taught us that our models are imprecise. It taught us that the universe does not always behave the way our equations predict. And it taught us, perhaps most importantly, that the gap between theory and practice can only be closed by doing, by building spacecraft, launching them at asteroids, and measuring what happens. The next chapter of this story will be written by Hera, and the chapter after that will be written by whatever mission succeeds Hera. Hera, perhaps the Neo-Surveyor space telescope, designed to discover and characterize near-Earth objects from an orbit near the Sun, where it can detect asteroids that approach Earth from the day side, the blind spot that current ground-based surveys cannot cover. The chapter after that may be written by a mission we have not yet imagined, targeting an asteroid we have not yet discovered, using technology we have not yet developed. But all of those future chapters depend on this one, on the story of Didymos, on the decision made in the early 21st century to stop merely watching the sky and start pushing back. There is one more dimension to this story that is rarely discussed, and it is perhaps the most profound of all. The DART mission was the first time in history that a species deliberately the orbit of a natural celestial body. That is not merely a technical milestone, it is a philosophical one. For all of human history, for all of the history of life on Earth, the orbits of the planets, moons and asteroids have been determined by gravity alone. No biological organism, no ecosystem, no civilization has ever had the power to change the trajectory of a world in space. The orbits of the celestial bodies have been, in the deepest sense, beyond the reach of life. They have been the fixed stage upon which the drama of biology played out. Immutable, impersonal, absolute. DART changed that. On September 26, 2022, the orbit of a celestial body was altered by a deliberate act of intelligence. The change was small, 32 minutes out of an orbital period of nearly 12 hours, but the principle is absolute. A species arose on a small rocky planet orbiting an ordinary yellow star in an unremarkable spiral galaxy, and that species reached out and moved another world. The implications of this capability are staggering when considered across long time scales. If humanity can move a 160-meter moonlet with a single spacecraft, then with enough spacecraft, enough time, and enough coordination, it could move larger objects. Not today, not soon, but eventually. The technology demonstrated by DART is, in principle, scalable. Multiple kinetic impactors, launched over years or decades, could incrementally alter the orbit of a larger asteroid, combined with gravity tractors, ion beam deflection, and, in extreme cases, nuclear standoff detonations. The toolkit of planetary defense could eventually extend to objects of any size. This means that the long-term future of Earth, the question of whether our planet will be struck by a catastrophic asteroid in the next million years, is no longer entirely a matter of chance. It is to some degree a matter of choice. Not today. The capability is rudimentary, but the principle has been established, and principles once established tend to develop. The philosopher Carl Sagan, who spent much of his career advocating for planetary defense and the search for near-Earth objects, once wrote about the deep time perspective that asteroid impacts force upon us. He argued that thinking about asteroid impacts requires us to think on timescales that are profoundly uncomfortable for human beings. Not years or decades, but centuries and millennia. It requires us to take seriously the possibility that the choices we make today, about funding, about research, about detection and deflection, will determine the fate of people who will not be born for generations. It requires us to care about a future we will never see. Didymos makes that abstraction concrete. It is not a thought experiment. It is a real asteroid with a real orbit and a real history of human interaction. The data from DART is not a simulation. It is a measurement, and the mission that will follow, Hera, is not a proposal. It is a spacecraft, already launched, already cruising through interplanetary space toward a rendezvous that will provide the next chapter of this story. The deeper truth about Didymos is not about the asteroid itself. It is about what the asteroid reveals about us. We are a species capable of looking billions of years into the past, reading the history of the solar system in the composition of a meteorite, the structure of a rubble pile, the orbit of a moonlet. And we are a species capable of looking centuries into the future, imagining threats that have not yet materialized, designing responses to hazards that may not occur in our lifetimes, and investing resources today to protect people who do not yet exist. That capacity, the ability to think across deep time, to act on behalf of the future, is, as far as we know, unique in the universe. No other species on Earth possesses it. No other civilization, if any exist elsewhere in the cosmos, has announced itself to us. We are, as far as we can tell, alone in our awareness and alone in our responsibility. And Didymos, this tumbling, boulder-strewn, sunlight-sculpted pile of ancient rock, is the object that forced us to confront that responsibility, not in theory, not in a thought experiment, but in the cold, practical reality of a spacecraft hurtling through the void at 14,000 miles per hour, aimed at a world that weighs 100,000 times more than itself, carrying with it the hopes and fears of an entire civilization. We have traveled a long way tonight. From the cold molecular cloud that birthed the solar system to the rubble-strewn surface of a moonlet struck by human ingenuity. From the ancient impacts that reshaped life on Earth to the single, deliberate impact that may have reshaped humanity's future. From the quiet discovery of a faint streak of light in 1996 to the thunderous silence of a signal lost in 2022. The story of Didymos is in many ways the story of us. A species learning to see the universe as it truly is, and struggling to respond to what it sees. What does it all mean? It means first that Earth is not safe. It has never been safe. The cratered surfaces of the Moon, Mercury and Mars tell a story of relentless bombardment stretching back 4.5 billion years. Earth has endured the same bombardment, softened only by its atmosphere and erased only by its geology. The next significant impact is not a question of if but when. The difference between the 21st century and all the centuries that came before is that we now have the tools to see the threat coming and, perhaps, the ability to avert it. That perhaps is the most important word in planetary defense. It is the gap between capability and certainty, between a single demonstrated experiment and a robust, tested, reliable defense system. DART demonstrated that kinetic deflection is physically possible. That is an enormous achievement. But physical possibility is not the same as operational readiness. The gap between DART and a real deflection campaign is measured in dozens of unsolved problems. Problems of detection, characterization, decision-making, international coordination, and engineering under pressure. Detection first. The Vera C. Rubin Observatory, currently under construction in Chile, will be the most powerful survey telescope ever built for discovering near-Earth objects. When it begins full operations, it will scan the entire visible sky every few nights, detecting objects far fainter and smaller than current surveys can reach. Within its first decade of operation, it is expected to discover the majority of near-Earth asteroids larger than 140 meters, the city killers, the objects that DART was designed to address. But discovery is only the beginning. Once a potentially hazardous asteroid is found, its orbit must be determined with extraordinary precision. A newly discovered asteroid might have an orbital uncertainty of millions of kilometers, meaning that its predicted position years in the future could be anywhere within a vast envelope of possibility. To determine whether it actually poses a threat, the orbit must be refined through repeated observations over months or years. And to plan a deflection mission, the orbit must be known with even greater precision, to the level of a few kilometers, over timescales of decades. This is where the problem becomes political as much as scientific. Imagine a scenario in which a newly discovered asteroid is calculated to have a 1% probability of impacting Earth in 20 years. 1%. That is simultaneously alarmingly high, orders of magnitude higher than the background impact probability for any given object, and reassuringly low. 99 times out of 100, the asteroid will miss. Do you launch a deflection mission? Do you spend billions of dollars to address a 1% threat? Who decides? What if the asteroid is 200 meters across and the impact would devastate a region the size of a small country? What if it is 500 meters across and the impact would affect an entire continent? These are not abstract questions. They are the real-world decision-making problems that planetary defense engineers and policymakers are grappling with today, and they do not have easy answers. The DART mission answered the engineering question, can we hit an asteroid? But it did not answer the governance question, who decides when to try? The international dimension adds further complexity. An asteroid impact does not respect national borders. A deflection mission launched by one nation benefits the entire planet, but the costs fall on the launching nation. If the deflection fails, or if it inadvertently shifts the impact point from one country to another, the geopolitical consequences could be severe. There is currently no international treaty, protocol, or institution with the authority to coordinate a global response to an asteroid threat. The United Nations Committee on the Peaceful Uses of Outer Space has established working groups on planetary defense, and the International Asteroid Warning Network provides a framework for sharing data about potentially hazardous asteroids. But these are advisory bodies, not decision-making authorities. In a real crisis, the chain of command would be improvised. This is the sobering context in which the DART achievement must be placed. The mission was a triumph of engineering and science, but it was conducted under ideal conditions: a known target, a safe test case, ample preparation time, no political urgency. A real asteroid emergency would look nothing like the DART mission. It would be discovered on short notice. Its properties would be poorly known. The decision to launch a deflection mission would be debated, contested, and second-guessed. The engineering would be rushed, and the consequence of failure would not be a disappointing data point. It would be a catastrophe. There is a particular challenge that haunts the planetary defense community, and it is worth dwelling on because it illustrates the kind of problem that no amount of technology can solve alone. It is the challenge of the last-minute discovery. Most planetary defense strategies assume years or decades of warning time. The kinetic impactor approach works best when the deflection is performed 10, 20, or 50 years before the projected impact. The deflection required is small, a nudge of millimeters per second, and the cumulative effect over many orbits is large. But what if the warning time is only months? What if a previously undetected asteroid is found on a collision course with Earth with less than a year of lead time? In that scenario, kinetic deflection may not be viable. The spacecraft must be designed, built, launched, and navigated to the target in a fraction of the time that DART required. The deflection needed would be much larger, requiring a much more massive impactor or multiple impacts, and the uncertainty in the outcome, already substantial for a well-characterized target, would be enormous for an object whose properties are largely unknown. This is the scenario in which nuclear standoff detonation becomes the option of last resort. A nuclear device detonated a few hundred meters from the surface of an asteroid could impart a much larger momentum change than a kinetic impactor, potentially deflecting even a large asteroid with short warning time. But nuclear deflection has never been tested. The physics is modeled but unverified. The political obstacles are formidable, and the risk of fragmentation, breaking the asteroid into multiple pieces, some of which might still impact Earth, is a genuine concern. The DART result provides some indirect guidance for this scenario. The high beta value of 3.6 suggests that rubble pile asteroids respond vigorously to impulsive forces. If a nuclear standoff detonation produces similar momentum enhancement, with the ablated surface material acting as ejector, augmenting the direct momentum transfer, then nuclear deflection might be more effective than the conservative models predict. But this is speculation, not measurement, and speculation is a thin foundation for a strategy that might need to work the first time it is tried, under the most extreme pressure imaginable. The reflection that emerges from the full Didymos story is not pessimistic, but it is sobering. Humanity has taken the first step toward defending itself against asteroid impacts. That step was necessary, courageous, and successful, but it was one step. The journey from a single demonstration to a comprehensive, reliable, globally coordinated defense system will require sustained commitment across generations. Commitment to detection, to characterization, to technology development, to international cooperation, and to the unglamorous, expensive, politically difficult work of preparedness. Didymos taught us that we can move an asteroid. What remains to be seen is whether we can move ourselves, move our institutions, our priorities, our political systems, quickly enough to turn that capability into a shield. The night sky has not changed. The asteroids are still out there, following their ancient orbits, indifferent to the small blue world that has just begun to notice them. But on that small blue world, something has changed. A machine was built, a target was chosen, a collision was achieved, a measurement was made, and for the first time in 4.5 billion years, the trajectory of a celestial body was altered by an act of will. That act of will is the beginning of a story whose ending has not been written. Whether it ends in survival or silence depends on choices that have not yet been made, by people who have not yet been born, in response to threats that have not yet been detected. The only certainty is that the choice exists. Before Didymos, it did not. Now it does. And that makes all the difference. Consider for a moment what the DART mission looked like from the outside. From the perspective of the cosmos itself, if the cosmos could observe. A small machine, assembled from aluminum and silicon and solar cells, carried across 11 million kilometers of empty space by a controlled explosion of kerosene and liquid oxygen, aimed at a pile of ancient boulders, barely held together by gravity, striking it at a speed that would cross the length of Manhattan in less than a second. The machine was destroyed. The boulders shifted. The orbit changed. And somewhere, on a small blue planet orbiting a middling yellow star, a room full of people cheered. From the outside, the event was almost absurdly tiny. The momentum transferred to Dimorphos by the DART impact was roughly equivalent to the momentum of a single raindrop falling on the hood of a car. The change in Dimorphos's orbital velocity, 2.7 millimeters per second, is slower than the hour hand of a clock. The mass of the spacecraft was less than 1/billionth the mass of its target. By any cosmic measure, the event was insignificant. And yet it was not insignificant. It was not insignificant because significance is not measured in megatons or kilometers per second. It is measured in understanding, in capability, in the transformation of a species from one that can only observe its own potential destruction to one that can, however modestly, intervene. That transformation is not a physical event. It is a conceptual one. And conceptual transformations, in the history of civilization, have always mattered more than physical ones. The discovery of fire did not change the amount of energy in the universe, but it changed everything about what one species could do with it. The invention of agriculture did not alter the biology of wheat, but it changed the trajectory of human civilization. And the DART impact did not significantly alter the orbit of Dimorphos, not on cosmic scales, but it changed the trajectory of human possibility. It opened a door that had been closed for 4.5 billion years, and walking through that door, committing to the work, the investment, the vigilance that planetary defense requires, is the challenge that now lies before us. Somewhere out there, in the cold and silent darkness between Mars and Jupiter, a pair of ancient rocks tumble through space together. The larger one, 780 meters across, spins once every 2.26 hours, its oblate body bulging at the equator, its surface strewn with boulders that have sat undisturbed for millions of years. The smaller one, barely 160 meters wide, orbits its companion at a distance you could cover in a 15-minute walk. Together, they trace an elliptical path around the Sun, a path that carries them from just inside Earth's orbit to well beyond the orbit of Mars, completing the circuit roughly every 2 years. They have been doing this for a very long time, long before humans existed, long before mammals existed, long before the first multicellular organisms appeared in Earth's ancient oceans. Didymos and Dimorphos have been traveling together through the inner solar system, silent witnesses to the entire history of complex life on Earth. And then, on a September evening in 2022, something changed. For the first time in 4.5 billion years, something from Earth reached them. A small machine, built by a species that has existed for the blink of a cosmic eye, crossed 11 million kilometers of void and struck the smaller body at 6.1 kilometers per second. The impact lasted a fraction of a second. The machine was obliterated. The debris plume expanded and faded. The orbital period of the moonlet shortened by 32 minutes, and then silence returned. From the perspective of the cosmos, the event was almost nothing. A tiny redistribution of momentum in a system so small that the entire Didymos binary would fit inside a moderately large sports stadium. A flash of kinetic energy dissipated in an instant. A microscopic alteration in an orbit that has endured for eons. But from the perspective of life on Earth, the event was everything. It was proof that a species born of stardust and water could reach across the void and change the path of a world. It was evidence that the same intelligence that discovered fire, invented writing, mapped the genome, and decoded the laws of physics could also be directed toward the most fundamental challenge of survival: the defense of the only home we have ever known against the blind, impersonal forces that have destroyed countless worlds before. The question posed by the title of this journey, what makes Didymos the most dangerous object nobody talks about, has an answer that is both simple and unsettling. Didymos itself is not, strictly speaking, dangerous. Its orbit does not bring it close enough to Earth for a collision in the foreseeable future. It was chosen as the dart target precisely because it is safe. But what Didymos represents is dangerous. It represents the reality that our solar system is populated by millions of rocky objects, many of them undiscovered, many of them rubble piles, whose behavior under deflection is poorly understood, and some of them, inevitably, mathematically, certainly, on orbits that will one day intersect with Earth's. Didymos is the laboratory in which we tested our first defense against that reality, and what we learned, that deflection works, but is more complex and less predictable than we assumed, is both reassuring and cautionary. We learned that rubble pile asteroids can be deflected by kinetic impact. We learned that the momentum enhancement from ejected debris can be several times greater than the direct momentum transfer. We learned that the surface of a rubble pile moonlet is a chaotic landscape of boulders with little fine material. We learned that our models, while approximately correct, significantly underestimated the effectiveness of the impact. And we learned that a single experiment, however successful, is not sufficient to build a comprehensive defense strategy. These are the facts. But there is a deeper lesson that transcends the data. The deeper lesson is that survival is not guaranteed. It never has been. The universe does not owe us a future. It does not protect us. It does not warn us. It simply operates according to its laws, the law of gravity, the law of inertia, the law of conservation of momentum, and if those laws align to send a rock toward our planet, the rock will come regardless of our wishes, our prayers, or our politics. What we have for the first time is agency, the ability to see the rock coming and do something about it, the ability to track its path, calculate its trajectory, design a response and execute it. That agency is new, it is fragile. It depends on telescopes that could be defunded, on space programs that could be cancelled, on international cooperation that could dissolve, on political will that could evaporate. Didymos is the reminder that agency, once discovered, must be maintained. It is the test case that proved the concept. It is the first data point in what must become a long and sustained campaign of preparation. And it is, above all, a mirror, reflecting back at us the question that the cosmos has always asked of every species that has ever lived on this planet: will you survive? The dinosaurs could not answer that question. They had no telescopes, no spacecraft, no understanding of orbital mechanics. When the Chicxulub impactor struck 66 million years ago, they had no warning and no defense. They were, in every sense, helpless before the forces of the universe. We are not helpless, not anymore. But being capable and being prepared are not the same thing. DART was a demonstration that we are capable. Whether we are prepared, whether we will invest the resources, build the systems, maintain the vigilance, and make the hard decisions required to turn a single experiment into a permanent defense, remains to be seen. The night sky is beautiful, it always has been. The stars are steady and calm, the planets trace their ancient paths, The moon rises and sets with reassuring regularity, and somewhere out there, invisible to the naked eye, a pair of ancient rocks tumble through the void together, one slightly changed, its orbit shortened by half an hour, its surface marked by the first deliberate impact from the one world in this solar system that has figured out how to push back. That push, that gentle, violent, improbable push, is the beginning of something. Whether it is the beginning of a new era of planetary defense or a one-time experiment that fades from memory depends entirely on us, on our choices, on our commitment, on our willingness to look up at the night sky and take seriously what we see. Didymos does not care what we do. It will continue tumbling through the void, following its orbit, indifferent to the small civilization that briefly touched its companion. The universe does not negotiate. It does not forgive. It does not wait. But for one brief, extraordinary moment, a species on a fragile blue world reached out across 11 million kilometers of emptiness and changed the path of another world. That is not a small thing. That may in fact be the most important thing we have ever done. And the silence of the cosmos, vast, patient, absolute, waits to see what we will do next.